Yes, we are on YouTube. Check. Good. Okay, Matt, you can copy paste the link from Zoom.
Yep. Yeah, I see that.
Okay, perfect.
No, I was just kind of curious logistically um, how that works. So registrations must have been pretty decent to open it up like that to the general public.
Yeah, we had more than 100 registrations, I think.
Oh, wow.
Hi, Matt.
Hi, Karina. How are you?
Good. How are you? Nice
Good.
to see you. Thank you for accepting to give this talk.
No, I'm excited. It is a good opportunity to uh, sort of talk about some of the work we've been doing, not in the mainstream ML or security communities.
Yeah, good. Great.
Are the speakers here already, Guna? Did you detect them?
Let's check. We have what? We have some here. We have. I don't think all of them are here now. I can see only the speaker for the second talk. The first and third one, I don't think they're here.
Yes, I think we're going to have the academic quarter, which is so popular in Italian universities. I don't know about US ones. What do you say, Matt? Do you also have this 15 minutes discrepancy between the defined start time for a lecture and the actual starting time?
A lot of people do. I'm a little bit of a stickler when it comes to starting on time. But yeah, I don't know. It seems like whenever I start 5 minutes late, I'll end 15 or 20 minutes late, and then everyone's really upset. So it's best to start on time and try and end sooner.
I see. People are joining in.
I'm unmuted, so
Try to stay and start talking. That's crazy. Go out and let's just stay. Can you guys see my screen?
Yes.
yes.
Right, it's 1 minute to 3 p.m. UTC time, and I think we can start this second session. Welcome to DeepTest 2020 again, for those of you who were in the first session, and welcome to the presenters from Americas second workshop on this interdisciplinary topic of testing deep learning systems and using deep learning to improve and enhance software testing. For the first time, the workshop is held virtually due to the COVID-19 outbreak. We hope you were all safe during these unprecedented times, and we are extremely happy to see you here today, even if not in person, in a physical meeting in beautiful Seoul. However, there is a number of people that made all of this possible and that I would like to thank now. So the part of the team in the top row is based in Switzerland, the beautiful city of Lugano. There is myself, Gennady Ranirova, and Vincenzo Riccio. We are all postdocs in the pre-crime group led by Professor Paolo Tonello, working on different aspects of testing deep learning-based systems. And that's why we got involved into this workshop. And in the bottom row are Professor Purino Pasaleano, Baishaki Vey, and Sarfraz Khurshid, who were the proponents of the first edition of DeepTest and kindly got us involved into organizing the second edition. So what are we going to talk about today? The topics in our call for abstract were quite heterogeneous, spanning from different aspects of testing and verification of deep learning-based systems. Actually, the topics that in the end got all the papers that got accepted are about like adequacy criteria for deep learning based systems and reinforcement learning systems. There was a talk this morning about the survey of deep learning for software prediction, and another one about using deep learning for learning developers' mistakes and fixes. But today we're gonna have one talk about test generation and another one about using deep learning to perform like model testing, model-based testing of simulated models. So as anticipated, the workshop is held in 2 different sessions due to different time bands of the people involved. Each session lasts approximately 3 hours. Today we're gonna have like the keynote by Matt Fredriksson, you, followed by 3 papers presentation, and the panel will like all the attendees can ask like several questions about the future and the progression of these fields. As for the questions, we're like we will manage them through the chat. So the session chair like will collect them and ask them to the presenters and the panelists. Other than that, we have no other guidelines other than common sense. And today we had like already like a session, and the participation was huge. We have more than 80 participants, divided as follows between like Zoom and YouTube. It was like quite insightful. We had like this very nice keynotes by Shin-Yu, who basically overviewed like his vision between like testing traditional software systems and DL-based systems. And after that, he presented like the research performed by his group on adequacy criteria for deep learning-based systems and other techniques, for instance, to repair a trained model to avoid misbehaviors. And in the end, what's more interesting for you, I guess, are the guidelines that that is suggested for future research. I'm not gonna, go in depth today because we got you covered and we recorded everything. After the keynote, we had the papers presentation, were like equally exciting, and a panel that raised a lot of interesting points, among which some are summarized here in the slide, like for instance, like the need for testing our techniques on real-world benchmarks other than image classifiers, and better techniques for explaining why the models are taking these predictions for developers and users. Another concern was like, how do we integrate these machine learning models that give this probabilistic output smoothly into existing software engineering processes. We're more talking about fairness and about avoid like over-engineer solution like for simple problems. And another like being concern that we faced and talked about was like the evolution of existing deep learning models that may be very good at solving the task that we are interested in today, but they necessarily need to evolve to reflect the change in the world. So as I said, the first session recording was recorded and streamed by YouTube and is available already. Whereas like we are live now with the second session, so you can share the link with your like colleagues, students, parents, grandparents, grandparents. And this is pretty much it. The last suggestion is like to let the people know that we are having a good time. So feel free to interact with us also on the social media, on our official Twitter account using our official hashtag. And now, without like further ado, I give the word to our session chair for today, Dr. Gunal Jahangirova. Thank you.
Thanks, Andrea. So as Andrea mentioned, I'm Gunal Jahangirova, and I work as a postdoctoral researcher at the pre-crime group in the Software Institute in Lugano, Switzerland. So I think we should start with our keynote. So it's my pleasure today to introduce our keynote speaker, Matt Fredrickson, who is an assistant professor in computer science department and in the Institute for Software Research at Carnegie Mellon University. Matt got his PhD and master's degree from the University of Wisconsin-Madison. And his main research interests are in security, privacy, and also in the applications of formal methods and programming languages towards building applications that are safer, less vulnerable, and more trustworthy. And one part of all these noble goals is fairness testing. So I think his research has an imminent outcome on making the world a better place. And in today's talk that's named How to Find Machine Learning Bugs That Expose Training Data and Bias Outcomes, Matt will tell us how his research can help humanity to fight all the kinds of horrible injustices, such as privacy violations and different kinds of discriminations.
Thank you, Gano. Let me see if I can share my slides here. All right. Okay, can everyone see just my presentation and not any surrounding windows?
Yes.
Yes.
Right. Thank you. And thanks for the introduction. So I guess the first thing to sort of address is, why am I here talking about, machine learning bugs that cause privacy issues and can potentially bias outcomes and lead to all sorts of unforeseen harms. Given that my sort of background and training and what I consider my academic home to be is kind of more in the security and privacy community. Well, the first sort of factor that I think partially explains this is that machine learning is so ubiquitous, right? And as a security and privacy researcher, anytime like a single technology is touching all sorts of application domains that sort of matter in the real world, right? So from credit decisions to who's going to get hired or be interviewed for a job or healthcare education, right? Machine learning is increasingly present in all of these domains. Right, and so whenever there's sort of wide use of a single technology, we start to ask questions about like what sorts of holes might exist or what sort of bad things might happen if we don't make sort of correct and responsible use of this technology. And one example that's getting a little bit dated, but I still like to use because it really is one of the things that sort of got me interested in looking at privacy issues in machine learning and kind of inspired some of the earlier work that I did in this space, was discussed in this New York Times article from like 2013 or 2014. They were talking about an advertising or marketing campaign that Target had been doing, where they were intentionally trying to predict whether some of their female shoppers were pregnant. Right? And if they were pregnant, then they were sending sort of physical flyers in the through the postal service to these customers, trying to sell them high price baby related items like diapers or prenatal vitamins and things like that. What was interesting about this wasn't necessarily that Target was trying to sell sort of high margin items like this to their customers through mailed flyers, but the way in which they went about learning which of their customers were likely to be pregnant, right? And this was sort of one of the earlier applications of machine learning that the press sort of started to take notice of and call into question these issues of privacy around its application. But basically, they sort of gave some examples of, more or less using people's shopping history, right? So whenever you go to a big box store like Target and make a purchase, they'll oftentimes ask you for your phone number or some sort of loyalty card so that they can track the purchases that you made in the past. And then they had some data scientists who were, analyzing these sequences of purchases and looking for sort of combinations or temporal orderings of things that allowed them to assign a pregnancy prediction score. So one sort of anecdotal example was some fictional shopper who bought, cocoa butter lotion, a purse large enough that I could double as a diaper bag, and some zinc and magnesium supplements, right? And they would conclude from this that there's a pretty good chance, like 87, 90%, that this person is pregnant, right? And then they would, of course, target them with flyers and bombard them with opportunities to purchase all of their wonderful goods. But the reason that this sort of came out as a privacy issue was this incident where they had sent one of these flyers to a teenage girl in Minnesota, one of the states in the Midwest here in the United States. And being a teenager, right, she was still living with her parents, and her father is the one who gets the mail. And he noticed that his 15 or 16-year-old daughter was getting these advertisements from Target that clearly had her pegged as someone who was pregnant, right? Who needed diapers and prenatal vitamins and things like that. So this father, calls up or writes a letter to Target corporate. He's pretty upset that that they were doing this, right? Concerned that Target somehow got the impression that his daughter was pregnant, and sort of brought this to the attention of the press. Right? Well, it turned out that Target was in fact correct, and a couple of weeks later, this father learned that his daughter, was in fact pregnant, and sort of apologized to Target and went on with his life. But this is an obvious privacy issue, right? Because this young woman lost her sort of right to control this information about her personal status, the fact that she's pregnant, and Target essentially outed her to her family, right, without any consent from her, or really without any kind of explicit disclosure of this sensitive fact about her health, right? And this might seem almost sort of expected or prosaic now that we're used to all the sort of impressive and interesting ways that machine learning models can infer things about people. But at the time, this genuinely surprised a lot of people, including myself, and I think sort of underscored the potential risks that this technology can have on individuals' privacy and right to control information about them and how it is used. So another sort of issue that complicates this issue of privacy in machine learning, and I think also touches very closely on fairness, is this idea that systems that make use of machine learning components substantially tend to be fairly opaque, right? So the idea is we have a bunch of data, we train a model to make good predictions because we don't know how to sort of write an application that can make those predictions using some domain theory or some deduction, right? We just have a bunch of data and we want to know how to get accurate predictions out of it. So if we have like a hiring model that we're deploying, right, that we've trained in this way, user data is going to go on one end and decisions are going to come out the other end, and we don't necessarily have a very good indication of the basis by which that hiring model is making its decisions, right? Is it going to prefer male or female candidates or candidates of a particular persuasion or ethnicity or something like that, right? Because we can't easily sort of open this opaque black box up and probe its internal logic. Right, and this came to a sort of high-profile head a couple of years ago when reports of this hiring tool that Amazon had been developing for several years was suddenly scrapped because they had discovered that it was issuing sort of biased predictions against female applicants, and they really didn't know how to address it or how to sort of repair this tool to get rid of this unwanted bias, right? So why was the tool biased against women? Well, Amazon being a tech company, like pretty much every other sort of large tech company in the United States or abroad, has primarily male-dominated headcount. So the training data that they were using to build this tool was heavily biased towards males. And I haven't looked at the internals of this recruiting tool, or I don't have any additional access to what was going on in the general public. But some anecdotes and for example, this Reuters article about it, when they started to sort of probe what was going on, they found that if somebody submitted a resume that had extracurriculars with the word like women's or female or something in it, that the tool would sort of dock the applicant some points, right? Or applicants who came from women's only colleges or universities tended to receive lower scores than even female applicants from co-ed institutions. Right, so the fact that the training data was heavily skewed towards males ended up sort of resulting in a model or a set of models that had learned that being a female made you less likely to be a good employee at one of these companies. Okay. So the sort of underlying view that I'll discuss today that I think touches on both of these problems in machine learning systems stems from looking at privacy and fairness violations as instances of harmful use of protected information. Right. So in the case of fairness or discrimination, we don't want our models to use variables like race or gender when we're making employment decisions, unless there's some kind of like business necessity exception, right? Like we're casting for a role in a movie that requires a female or somebody from a particular background. In cases like that, maybe it's okay. Right? When it comes to privacy, if we're doing marketing, we don't want to use health or political background or religion or something like that. We're making decisions about which impressions to show our users, as this sort of violates people's normative expectations, and in some parts of the world does indeed run afoul of privacy regulations, right? And sort of compounding this problem uniquely in systems that use machine learning. Is this issue of opacity, right? We don't really know how the systems are functioning or what their basis for making predictions or decisions is. Then it's hard for the developers of the system to know how their users' information is being used to make these predictions. And of course, on the other end, if I'm an auditor, either internal or for some government or regulatory agency, this opacity makes it difficult for me to check compliance, or if somebody comes to me with a claimed violation, can make it difficult to actually verify the claim. And these two factors together sort of, I think, turn out to be a pretty big disincentive for a lot of potential users of machine learning. Organizations that could benefit from using these systems, right, are sort of discouraged from doing so for fear of running afoul of their users' privacy expectations or fairness regulations or something like that. So just to give you an idea of what I'll discuss today, in the first part of the talk, I'll describe some general principles and techniques that my group and I have been developing over the past several years to sort of help get a handle on how machine learning models do make use of protected information. And then I'll talk about two sort of salient examples of bugs that can crop up in machine learning models that I think sort of exemplify either the sort of misuse of of available information, or sort of showcase some of the techniques we've been developing and how they can be used to uncover these bugs in practice. And I do have the chat window up, so if anyone has a question, please type it in, and I'll try to keep an eye on it and answer as we go along. Okay, so the sort of key idea that I think, you know, pretty much any effort to characterize how a machine learning model uses you know, people's protected information is this idea of a causal intervention. And what we really want to get at is sort of how important is a piece of information in the prediction that was issued. So suppose that we have somebody who applies for a loan, and they're subjected to this you know, fairly simplistic credit model that takes as variables their age and income, but for whatever reason, you know, only uses their income. And this person is denied, and they want to know, you know, what was salient? Was it you know, because I'm over the age of 50, and this model thinks that my potential earnings in the future are going to be low, because that would be problematic, or is it because my income just doesn't meet whatever threshold this institution believes that I need to have to be a good credit risk? Right? So if we want to know which of these variables or sort of relatively how important they are in the decision, then we can intervene on each one in isolation, right, and look at how the model's outcomes change, right? And this will give us an idea of how much you know, actual causal influence these inputs have on this person's individual decision. So basically, if we keep income fixed and change age, then because this classifier only uses income in its decision, right, our decision will stay the same. We'll still see a denial, even though we're sort of flipping the age that we're handing to it and giving it different values. On the other hand, of course, if I keep age fixed and I change income, then I should see, if I'm doing this reasonably well, then I should see changes in the decision that the classifier issues, right? And that tells me that the factor that is most influential in this model's behavior is income, at least when it comes to the features that I've given this model. Okay. So this is the sort of main idea behind a growing set of techniques that are called attribution methods. And these are becoming a popular way of explaining the behavior of machine learning models on individual instances. So some example sort of implementations of these methods are in this library SHOP, which Scott Lumberg and his collaborators at University of Washington have been developing for some time. And more recently, in a library called Captum, which is part of the PyTorch sort of repository for explaining predictions of deep learning models. And there are lots of ways that these attribution methods can assign importance to individual features. Right? So SHOP makes use of both causal and associative techniques for measuring the importance of features on you know, both sort of more traditional models like random forests or decision trees or boosted forest or something like that. And Captum is more focused on you know, gradient-based methods for deep models. And you've probably seen examples of the sorts of explanations that these attribution methods give you, like on image models. One way of sort of interpreting the attribution mapping that you get from these techniques would be to sort of do an intensity overlay on the individual instances. So here's an example of a facial recognition classifier applied to some instances from labeled faces in the wild. And this uses a gradient-based attribution method that I'll get back to later in the talk. So this is all well and good when it comes to addressing our original problem of understanding protected information use in models, as long as the information type that we're concerned about is explicitly given as an input feature to the model. But very often it is not the case that the thing we care about is provided directly as an input, right? So even in the sort of aging and more historical example of this target classifier, there obviously was no sort of pregnancy feature. That's what they're trying to predict. Rather, the model was given a whole bunch of sort of correlated features, and it inferred pregnancy status from those. And this is even more obvious, I think, when it comes to deep neural networks that are most effective at tasks that take as input images, so like pixels individually would be the features, or language models or audio or something like that. None of these sort of low-level features that we're giving to the deep network individually characterize the protected information type that we want to know about for privacy or fairness. Instead, the model sort of learns a way of mapping those low-level features into representation that is essentially a proxy for the protected thing that we care about, right? So we call this proxy use of protected information. And this is really the sort of key challenge to address when it comes to understanding information use in the sort of common case of models that don't take sensitive attributes in by default. So taking a closer look, what exactly do we mean by proxy use? Well, what we want to characterize here is really a strict generalization of explicit information use. So we'll consider as a case of proxy use situations where the model does take the explicit attribute in, right? But of course, we also want to characterize inferred use, right? So from the anecdote about Target at the beginning, prenatal vitamins and a blue rug were a sort of weak to middling proxy for pregnancy status. So we want to understand when models are inferring protected information types from other features, right? But simply inferring a protected information type isn't always enough. That's sort of a weak criteria to apply. Because it could very well be that just by chance the model infers something that we deem sensitive, but that inference is never used in any substantial way, right? So it's not actually influential on the model's ultimate prediction, right? So in this sort of decision tree on the right, the model infers the same thing twice, but its outcome is the same either way, sort of regardless of which direction that inference goes. The model always outputs the same thing. So this would be an example of a case that we probably want to ignore. So with this sort of intuitive characterization, we can start to get a bit more formal and perhaps try and axiomatize what we mean by any suitable definition of proxy use. So first axiom, explicit use is proxy use. If a protected variable is an influential input of the model, then we say that model has proxy use. But to account for these cases of inferred use, we also want to consider sort of proxified preprocessing of sensitive variables as valid instances as well. So if you imagine that we have some model that makes explicit use of a protected variable, and we sort of compose that model with a different one that infers the protected information type, right? So that now this sort of composed model doesn't take as a direct input the protected information, but instead it's where in the whole, where the protected information variable would have been, we now have some pre-processing computation that infers the protected type from other features. We want to consider this to be proxy use as well. Okay, then a dummy axiom seems necessary. So if we have a model that makes proxy use of our target information type, and we add some other variable to it that isn't really influential in its behavior, then that doesn't really change the fact that this model, has proxy use. And finally, an axiom that allows us to ignore sort of irrelevant cases if our protected information type is statistically independent of all of the inputs of the model, right? Then there's really no way that that model can make proxy use of our protected type Z. Right? And we want to make sure that that model isn't deemed to have proxy use. So these four axioms seem, intuitively to sort of capture what we want out of a reasonable definition of this type of behavior. But unfortunately, these axioms are inconsistent. Right? So when we were, first doing this work, and we thought that we were on the right track, and one of the PhD students sort of observed that these four axioms cannot be mutually satisfied. We were a little bit sort of lost in the woods for a while. So the sort of intuition behind why these axioms don't play well together, is based on this idea of functional composition. So basically, with this pre-processing axiom, we're sort of forced to preserve proxy use under this very general and powerful notion of functional composition. But there's no, or there wasn't any good way that we could find to sort of characterize what the rest of the model did after that composition happened, right? So the rest of the model could cancel whatever proxy we were introducing, right? Ultimately leading to an outcome that is independent of the data type that we're concerned about, right? Conflicting with our independence axiom. So the way that we addressed this was, instead of using like pure functional composition, we took a more syntactic approach and characterized proxy use in terms of syntactic composition. So what we mean by this is we sort of tie proxy use directly to how our machine learning model is represented as a program. Right? So if a model has proxy use, then we ought to be able to sort of identify some subset of some component in the program that's responsible for the proxy use. Right? So that seems like a bit of a windfall. Having witnesses is going to be useful in debugging and understanding and explaining these instances. But of course, the downside to this is that checking proxy use now requires sort of white box access to the model. We need to be able to open it up and see how it's represented and sort of understand its intermediate states and its intermediate semantics in order to make a judgment about proxy use. Okay, so the sort of notion of syntactic composition that is relevant here is really decomposition. So if I'm given some model P represented as a program, we sort of characterize this class of possible ways of decomposing this syntactic object into two models and some fresh free variable X, so that replacing that free variable with the proxy P1 inside of P2 gives us something that is equivalent to our original model. Okay. So easiest to see this sort of in by example with decision trees. If we have this simple sort of two-level test on years in job and whether somebody has an unpaid mortgage, we can decompose this into P1 and P2. We think of P1 as a potential proxy, a sort of subcomputation that might be correlated with protected information type. and P2 as the sort of context with this free variable X that we can sub P1 in for. Right, and with this type of composition, we can define proxy use of a random variable Z in terms of the existence of an influential decomposition. So a decomposition that is causally influential on its enclosing context P1. And we also require that that decomposition is statistically associated, somehow correlated with the protected information type. So in order to kind of apply this framework and understand how a model is making use of protected information, we need to decide on three things. First of all, the space of possible decompositions. In a lot of cases, there are several ways that we might think of decomposing models, and we'll see some examples shortly. And then a measure of causal influence. Basically, how are we actually going to quantify causal effect of a potential proxy on the model's prediction. And thirdly, a measure of association. And I won't talk too much more about the measure of association. You can usually apply something kind of standard from information theory, like mutual information or variation of information. Or if you only care about linear relationships, then you can maybe just look at correlation coefficient or something like that. But these first 2 points, I think, are a little more interesting because they can change to a surprising degree depending on the type of model that you want to understand. So we'll take a look at the sort of first class of models that we studied in a CCS paper from 2017. We're primarily focused on what I'll call, for lack of a better term, functional models, things that you could sort of imagine as being represented by functional terms that might have some branching. So like decision trees, random forests, rule lists, things of this sort. So some branching structure combined with like relational tests on individual features or groups of features are the sorts of models that we're concerned with here. And the way the way that we propose decomposing these uses the model's representation as an abstract syntax tree. Right, so a potential proxy is just some subtree in the model's AST, and the P2 component of the decomposition is the enclosing context. Right? Sort of like the examples that I showed previously. And with this sort of mode of decomposition, we can characterize influence in a way that is a pretty direct generalization of the causal influence measures on model inputs. But instead of intervening directly on the input to the model, now we're sort of intervening on the model's intermediate state at the point at which we decomposed it. Right, so the influence is really, you can think it is the probability that sort of a random change to the potential proxy, to the subcomputation, leads to a different final response in the ultimate model. And we have to be a little bit careful about the sort of random spaces that we use to quantify this over. Like in the context of Boolean function analysis, people have talked about similar kinds of influence measures in the past, but typically the randomness was uniform. Here we're concerned about random changes under the sort of target distribution that we want to apply the model to. So we draw the inputs randomly from the target training or test or whatever distribution that we're concerned about, right? So to compute this, you can just think of like I can draw two samples from my test distribution, X and X prime. I evaluate the entire model on one of them. And then on the other, with the other instance x prime, I evaluate just the subcomputation. And then the intervention is plugging the sort of outcome of that evaluation into the context model P2, where we left that free variable, and then evaluating the rest of P2 on the original instance. So soon after looking into these functional models, we started to get curious about generalizing, eventually to deep neural networks. But first we wanted to make sure that the sort of simplest kind of continuous model made sense with this story. So the next step was looking at linear models over continuous real data. And this was sort of summarized in a Nurem's paper from 2018. So linear model you could think of as one of these sort of functional terms. You can certainly represent it as a flat or nested sum of scalar multiplication by multiplication of one of the input variables. But immediately see that there are some potential problems here. Because for the behavior of a linear model, it doesn't really matter sort of how I might happen to represent it as a functional term, right? So say I represent it as a functional term where addition is always a binary operation, then I have to choose some way of associating these additions with each other. And depending on the choices that I make there, I could end up with a completely different set of possible decompositions, and therefore a completely different set of potential proxies than if I had grouped the terms differently with each other. Right? But at the end of the day, this doesn't really matter for a linear model because regardless of how I group the terms, it's always computing the same thing, right? So we do need to take somewhat of a different approach. The next sort of most obvious thing to do would be to, quote unquote, ignore the associative groupings and possible like commutative permutations by defining decompositions, as a set of all possible equivalent groupings under associativity and commutativity. But even this doesn't quite seem adequate, right? And I think this is best explained by looking at a picture. So with a linear model, you can sort of think of the combinations of the terms in a vector space, right? And if we have a model that is like alpha1 x1 plus alpha2 x2, that looks sort of like this, we might say we're interested in proxies that have influence beyond a particular threshold. And in this sort of viewing of the semantics of linear model, influence would be characterized by the length of a vector, right? So the sort of white circle depicted here corresponds to the influence threshold that we care about, and the association in this sort of view of these models is characterized by the angle of vectors, or the angle between some vector representing projected information type Z and some component of the model. So say that the sort of sensitive associations are characterized by the pink region of this diagram. Then if we only consider as decompositions either alpha1 x1 or alpha2 x2 or alpha1 x1 plus alpha2 x2, and so basically all of the possible combinations of the individual monomials, then this model does not have proxy use, right? Because the only vectors that correspond to that set are the corners of this parallelogram, right? But indeed, if we sort of think of decompositions as corresponding to like partial sums of these monomials, then this model would have proxy use, right? And that's depicted by this vector in the middle here that exceeds the influence threshold and fits within the association region that we care about, right? So long story short, the space of decompositions that we consider for linear models are weighted sums of the model's terms, right? So the beta sub i's are values between 0 and 1. So that would make the potential proxy sort of submodel some weighted sum possibly comprising the entire model, and P2 just the difference between the entire model and that weighted sum. This leads to a characterization of influence that is really nice to work with because it's directly proportional to the variance of the decomposition, right? You'll note that at first we're a little surprised by this because variance doesn't seem like it has anything to do with causal influence. And we detail this in the NeurIPS paper. If you sort of like trace this definition back to similar axioms to the ones that we used in the CCS paper, this does indeed sort of agree with what we were getting at originally. All right, so finally, how do we apply this framework to deep neural networks? Well, the sort of perspective that we take is this view of a network as a composition of a feature extractor, right? So whatever happens in the first or bottommost like n layers of a network, and some classifier that uses the sort of internal feature representation produced by that extractor. So then a decomposition is just some slice of the network that sort of bottlenecks it or partitions it into two parts. Right? Importantly, like there's absolutely no reason that we can't think of this decomposition as corresponding to a subset of the features or a subset of the neurons at some internal layer. And indeed that in our experiences is the most useful way to go about this. So then when it comes to influence, again, sort of starting from the same or similar axioms that we had looked at in the simplest case of our functional models, the measure that sort of uniquely makes the most sense here is this aggregation of gradients of the internal sort of submodel P2's influence on the or P1's influence on the output of P2. So the gradient of P2 with respect to X, where X is the internal representation of our potential proxy, right? And then this is all weighted by the data distribution. So you can really think of this as an expected value of the gradient of the model's output with respect to the internal representation that we're interested in testing for proxiness. Right? And just a quick note, so this influence measure is quite general. So depending on like how you choose this data distribution and a few other choices about, for example, how you post-process the model's output, you can recover several sort of gradient-based attribution methods that are in popular use now. But the sort of key difference is whereas most gradient-based attribution methods focus solely on attributions for explicit inputs, this measure makes sense on internal representations, and so works for our purposes in testing for proxy use. Okay, so now that we know how to sort of specify what proxy use means in a wide range of models, how do we actually go about finding it or testing for it or verifying it or whatever verb you you prefer. Right, so just a reminder, our goal here is to find ways of decomposing the model so that some sort of internal component is highly associated with some protected variable, race or gender or political status or something like that, and also very influential on the model's final outcome. Right? So the most obvious, direct, and in some ways satisfactory way to go about doing this, if your model isn't too large, is just to do a brute force search. Sort of iterate over all the possible ways of decomposing the model, measure their statistical association with your protected variable, and then measure their influence. And if you do this exhaustive audit and you don't find any proxy use, then that's a pretty convincing result. You know, as long as you're happy with the sort of choice of how you decompose things and how you measure influence and so forth. And this is also very easy to implement, like especially in a language like Python. So it's you know just a couple of dozen lines to be able to do this on like a wide range of scikit-learn models and so forth. The obvious drawback is this is quite costly. It only works, you know, you can only do an exhaustive search if you have a finite number of decompositions to search over. That obviously is not the case with linear models, for example. While it might be the case with the way that we propose decomposing deep neural networks, there are, you know, it's still just far too costly to even imagine doing this on a reasonably large model. So another way we've looked at going about this that was discussed in the NeurIPS 18 paper on proxies and linear models is to frame it as an optimization problem. So basically, you know, find a way of specifying proxy use as some kind of numeric objective. The way that we went about it was to objectify association and then frame a constrained optimization problem where a minimal sort of influence threshold was the constraint that we wanted to satisfy, and then minimize it to find the strongest offending proxy in the model. And of course, if you have like a convex problem, as we showed how to do with linear models, and you don't find a proxy that is strong enough to be concerned about, then this is a pretty convincing way to go about things as well. And it's quite efficient. Again, if you can frame this as a convex problem and your model isn't extremely large, you can also benefit from, you know, very rich space of existing optimization tools. So there are a lot of benefits to this approach to finding proxy use, but the drawbacks are important as well. So none of the optimization-based procedures that we have explored for this problem are complete, in the sense that like even in the case of linear models where we can frame this as a convex objective, we end up over approximating the sort of space of possible proxies, and there really isn't a good way of you know, if you find a potential proxy of actually verifying that is indeed a proxy without doing some fairly expensive post-processing on it. And of course, this only works on continuous models. Even with deep neural networks, which operate over continuous data, the space of decompositions is discrete. So there is no like obvious way to apply this directly to even deep neural networks at the moment. All right, so I did want to mention one other way of possibly finding proxies in models, pretty much any model, because this is a black box approach that is based on generating sort of promising pairs of test instances that might surface proxy discrimination. And so this is based on this idea that you know, if I give my data to a model and get an outcome that I'm not happy with, right? The natural question to ask is, you know, if I had a different protected attribute, so if my gender were different or my ethnicity were different or something, then would my outcome have been the same, right? You know, if we can operationalize that question and find a satisfactory way of like generating a hypothetical, like counterfactual version of me, or somebody who we wish to audit, then answers to this question might sort of indicate whether the model was making likely proxy use. So one way of accomplishing this, you know, is to take a very sort of formal causal approach and assume that we have a detailed, like, causal domain model of how you know, latent factors and features generate other features, and then intervene on the sensitive attribute that we care about. So this is basically the approach that Kushner et al. Have described in this framework called counterfactual fairness, which appeared at, I think, originally at NeurIPS in 2017 and several times since. And so basically, if you can do this intervention, generate counterfactual versions of people, then you can start to, you know, test the model a bit more extensively and see if its outcome flips consistently when subjected to pairs that are equivalent, but for this intervention on the protected attribute. And if you do find evidence of proxy discrimination here, then, you know, perhaps you can make use of explainability tools or other sort of white box methods that can, like, zero in on like the influential components of the model, or give you more information about, you know, what exactly is going on in these cases where the model appears to be discriminating. But the downside here, of course, is, like, causal models are very hard to come by. It's not too often that you're going to get, like, a perfect sort of domain theoretic functional description of how features are generated from latent variables and randomness. And even if you do have it, actually performing this intervention can still be quite expensive. So an approach that we've been exploring recently is to instead use optimal transport theory to compute these. I don't want to call them counterfactual anymore because there really is no notion of causality at play, but sort of corresponding pairs of inputs. So the idea is to construct a mapping that moves the mass from one distribution, say the distribution of female job applicants, to another distribution, like the distribution of male job applicants. You want to construct this mapping in a way that minimizes some cost, right? So you want a way of transporting the mass from one distribution to another in a way that sort of requires least effort, or is the most, you know, generates the most plausible pairs, would, I think, be the right intuition for this domain. And so this is called the optimal transport mapping. And one sort of nice thing is, you know, it's based, computing this mapping is based on this cost function. This can be a domain specific thing that sort of encodes whatever available information you have about the type of data that you're looking at. But if you don't have such information, in our experience, oftentimes using a generic metric, like some LP metric, works reasonably well in practice at surfacing instances of discrimination. And there are lots of ways of constructing these mappings, say by solving a linear program, although this doesn't work too well if you have a lot of data, because even if there are nice tools for solving LPs, the size of the LP is quadratic in the number of data elements you have. So this only works for small models, or a direction that we have spent more time exploring is training generative models, say like GANs or autoencoders or something of that sort, using objectives that coincide with this optimal transport mapping criteria. Okay, so I'll quickly walk through an example of like how this works on a toy data set that this paper that my colleagues at Carnegie Mellon, Zach Lipton and Alex Choldakova wrote a couple of years ago to sort of demonstrate what can happen in cases where you even seem to have a model that is behaving fairly. So they constructed this synthetic data set that has two features, hair length and work experience, and then considered, training a demographically fair model that predicted like, job worthiness based on these two features. The idea is like this model isn't given gender, right? And it's trained with a fair objective, and it achieves demographic parity, so it appears to be fair. But kind of surprising things can happen with how the model uses these available features that are exemplified really well by this optimal transport technique. So what we're looking at here is, first of all, the line would be the decision boundary of this fair model, and then the four sets of points correspond to individuals whose decisions flipped after being processed by this optimal transport mapping. So in the first case, this F minus set, this corresponds to the red minuses that turn into blue minuses. These are female applicants who were originally denied a job interview or a job offer or whatever. And what's clear from looking at the results of this mapping is that these women seem to have been denied because of their work experience, right? Because their male counterparts, these blue minuses, are predicted positively, and the most substantial thing to have changed was their work experience. And that seems all well and good. Denying someone a job based on their lack of experience is arguably legitimate, except for when we sort of compare them to this other set of female applicants, F plus, the red pluses that turn into blue pluses, who seem to have been hired because of their hair length, right? So before, when we look at their original features, they were mapped to positive outcomes by the model. Their sort of corresponding inputs under this optimal transport mapping are denied a job, and the most substantial factor to have changed was their hair length. Right? So despite having this sort of apparently group fair prediction model, sort of studying its behavior under pairs of test inputs generated using this optimal transport technique, sort of surfaces the somewhat surprising, I think, and subtle ways in which the model, is still biased on a sort of subgroup or more individualized level. Okay, so this is obviously a toy data set, but we have applied this technique to several more interesting and more realistic sort of scenarios that we write about in our recent FATSTAR paper. So if you found this interesting, I'd encourage you to take a closer look at that. Okay, so that does it for protected information use and predictive models. How am I doing on time? I know we got started a little late. Do I have? Yeah.
I think you have a couple of more minutes, yes.
Okay, so I think I'll quickly go over featureized bias amplification, and then maybe just briefly touch on privacy risk, but I don't want to bleed too much into the next speaker's time. So okay. Bias amplification. This is a relatively recent problem that we started to get really interested in after reading this paper by Zhao et al., which was like the best paper at EMNLP in 2017. It had a rather memorable title. It's like Men Also Like Shopping, exploring gender bias amplification and label prediction tasks. But the idea here is simple and seems so apparently like a buggy behavior that it was impossible for us to not like take a closer look at it. What they observed was in this like MS COCO like object classification and context data set, in the training data, you know, about 2/3 of the images that are labeled cooking have women agents in them. But when they're training prediction models, 84% of the agent roles that were predicted in these cooking images were labeled as women. So they start out with a data set that's already fairly biased when it comes to like which sex appears in cooking pictures. And consistently they were finding models that like, you know, took that bias and just ran with it to a pretty surprising extent. And so when we sort of started to follow up and look at other data sets and other types of models and so forth, you know, we were convinced that this was not something that was quirky or different about this particular type of data or this classification task. This you know, indeed is something that seems to happen fairly consistently, you know, in particular with deep models, but also even with fairly simple linear models. But the first thing to sort of point out here is that, you know, this isn't always a bug. In some cases, bias amplification is unavoidable unless you're okay with sacrificing some predictive accuracy. And so to sort of understand why this would be the case, a simple example type of setting would be one where we have a binary prediction task, and our features are IAD Gaussians with means that are a function of the response label. And in this case, right, so basically you can think of like two Gaussian blobs that are separated with means that are separated by some distance. And in this case, the amount of bias amplification in a Bayes optimal sort of prediction model, right? So minimizing our expected prediction loss is a pretty straightforward function of the statistical distance between the means and the class prevalence, right? So basically like what this function looks like is depicted here. So the different curves are settings where the means are separated by varying amounts, with the sharpest curve being means that are the closest together. You can see that when my sort of class prevalence, P star, climbs even just a little bit when the means are close, like goes up to 0.6, I'm already amplifying that prior bias about as much as I possibly can. So this curve flattens out basically when the class prevalence plus the amplification, you know, is 1. That's what that line is. There's basically no way to be more biased. The model is essentially always predicting, you know, one class or the other in expectation, no matter what. The sort of intuition here is when, you know, in this kind of a setting, when the means are very close together, the label prior is more informative than the features are. Right, so the model is better off just looking at the class prevalence in its training data and biasing its responses most heavily on that than anything that the features could be telling it. Right? So in some cases, this isn't really a bug. It's just a sort of function of whatever type of model we're trying to create and the characteristics of the data that we are classifying. But indeed, in some cases, we found it is, and to understand why, it's sort of necessary to look at the way that the model is making use of the features that are available to it. And this is work appearing in iClear last year, by the way. So if we go back to this MS COCO data set and these sort of anecdotes about you know, men and women in cooking pictures. One sort of observation is in this data set, because 2/3 of the training instances of people cooking have women in them, sort of visual features that tend to appear in cooking settings, kitchens or outdoor grilling patios or whatever, are weak proxies for gender, right? Because like one of the prediction tasks the model is is trained for is predicting gender, right? These basically work out to be weak features. And the sort of observation is that if the model places too much influence on these like weakly predicted features, right? So like a refrigerator appears in a lot of kitchens, and the model might learn that because women are in this training set more frequently present in these kitchen pictures, whenever I see a refrigerator or a stove or something like that, like that's evidence for there being a woman agent in this picture. And if the model sort of places too much weight on weak features like that, then that can explain some of this like unnecessary bias amplification. In particular, if one class has a larger prevalence of these weak features that are sort of associated with it, then that's when we see bias amplification happening sort of in its strongest form. So this graph on the bottom of my slide is some synthetic data where we sort of artificially just kept adding more weak features that were associated with one class and not the other. And especially if there wasn't very much data available to train on the sample, then this effect ramps up quickly and stays persistent. One sort of
sorry, if I may interrupt, we are out of time, so if you could wrap up a bit quickly.
Okay. Yeah. Okay. So basically, you can understand bias amplification by looking at the influence of these weak features, and you can actually address a lot of the problem we found by feature pruning. So I won't talk about privacy. I'll just go to my summary here.
We can talk more about some of these concerns in the panel later.
Yeah, that's good.
Like more time for asking a couple of questions from the audience.
Yep. Okay. All right. So basically, you're attending this workshop, so you know that machine learning systems are being widely used and to make sort of important sensitive decisions. And the fact that we can't really we don't really have a good way of understanding how they're behaving or what they're doing introduces some interesting problems. The sort of takeaway message here is getting a better handle on how especially sensitive information is used by models can address a lot of these problems, and both explain to developers what's going on and point to mitigations, but also provide good ways of sort of auditing them both internally before deployment and sort of in a black box kind of situation once they're already out in the wild. All right.
Thank you. Thanks a lot. So we have one question from Michael Weiss. He asks that in practice, I'd assume that many input attributes are quasi-redundant. For example, is male bot men's aftershave bot tie? Does this pose a problem for your flipping logic to identify the critical attributes? If so, any idea on how this could be addressed? Yeah, so that's an interesting question, and like I agree, in a lot of cases, especially where we're applying deep models, you're going to have a lot of input attributes that all sort of like point to the same label or associated with a similar thing. I guess I don't really. Maybe Michael, if he's, I don't know if he's on YouTube or the Zoom, if he would care to elaborate on why he thinks that would necessarily pose a problem. But I might be able to answer his question a bit more satisfactorily. I
am here.
Yeah.
So it's possible that I misunderstood the approach slightly, but the way I was thinking about it is like basically I think you brought the example that you flip one attribute and then you see whether kind of the output changes. Yes. And if you have these redundant inputs, especially in like deep learning and stuff with the well-regularized models, if you flip one attribute, the model should be properly trained to actually not taking this noise into account, but rely on the other redundant attributes. So in that case, even though the attribute is critical, so it is a male, the prediction would not change. So that was the origin of my question.
Yeah. Okay, so I first of all, I misunderstood your question. I thought you were talking about the optimal transport work. You're talking about like causal attribution methods.
Exactly. Yes.
Yeah. No. I think that is one of the like primary motivations for looking at proxy use to begin with. So,
okay.
Like in this case, none of these features like are a feature that directly encodes gender, except for maybe is male, right?
Yes.
Yeah, that one is hard to get around. But supposing that you only have sort of things that are just associated with gender, men's aftershave, bot tie, etc. And what you really care about is whether the model is inferring whether I'm a male or using like my maleness. Then that's exactly what we're trying to address with proxy use. Like presumably in a situation like that, like my model would have some structure where all of these sort of individual kind of quasi-redundant features are aggregated, and if the model is using them to predict my gender, and that's pertinent to one of its outcomes, then identifying like that aggregation and pointing out like where it is happening, how it is happening, is the problem that we're trying to address. But now, like say that the model had a direct gender attribute is male, and then a bunch of these sort of quasi-redundant features alongside it, then absolutely just like flipping, even the gender feature doesn't make any sense, right? And really, like I think the problem that you're introducing, if you do directly try to do that, is like you're not really being faithful to the distribution that the model is trained to make predictions on. Like you're not going to see an instance naturally in that distribution that has its is male feature set to false, but like all of these quasi-redundant gender features consistently pointing to male. And in a case like that, yeah, you have to take a different approach. So we didn't really talk about it here, but this optimal transport mapping is one way of addressing that.
Okay.
Because like this mapping will give you, its image will be the distribution that you want to map to. So it like accounts for sort of organically the relationships between these features as it pertains to like going between distribution of male and female.
Okay. Thank you.
I have one question. So from the examples you've been showing, I got an impression that the approaches you're describing are applicable mostly to decision-making systems. And I wanted to ask whether this can be applied, for example, to the automated translation. For example, if you translate from gender-neutral languages to the ones that have he and she, you can see that things can become a bit discriminative. Can these approaches be applied to those cases or not?
Yeah, that is an excellent question, and to be perfectly honest, not really a class of problems that we've spent much time looking at. So like if I understand, you're talking less about like classification or regression type models and more about like generative models, right? Yeah. So certainly. Like when it comes to characterizing influence on a model like that, you probably need to start from scratch and think about like what the right properties of an influence metric there would be, and because like all of these methods are sort of like based on this idea of being able to measure causal influence and so forth. yeah, I think that like we'd probably want to sort of start from square one, and then see, you know, if we had a good way of measuring causation in these models, you know, what techniques that we built on top of our previous influence metrics sort of could be preserved and carried over with minimal effort. But it's not to say that I think that there aren't serious privacy and fairness issues there. I'm certain that there are, and you know, I'd love to spend time thinking about it, but there's just too many problems to potentially focus on.
Okay, so I think we should stop here. There is one more question, but we can maybe discuss it during the panel. So we can maybe take a very short break of 2 minutes and come back for the talks. Thank you. Thanks a lot.
Thanks.
So I think we can continue now. So I would like to introduce our next speaker. So our next talk is manifold-based test generation for image classifiers, and it will be presented by Tai-Jun Byun. Tai-Jun will tell us about their approach, which generates both test inputs, but also the labels for those test inputs. So this kind of frees us from this metamorphic relationship being used as an oracle that have been mentioned many times during the first session today as an inherent limitation. So please, Tai-Jun, go ahead.
All right, thank you for the introduction. Do you see the screen all right and hear my voice?
Yes, perfectly.
All right, thank you. Hello, I'm Tai-Jun Byun from University of Minnesota. This is a work together with my co-advisors, Anjay Rayadugam, and also in collaboration with the companies like Collins Aerospace and Boeing. So thank you for inviting me, first of all. And this is going to be a brief introduction of the several papers that our group has been publishing and also some of the ongoing works. So the title, Manifold-Based Test Generation, this paper is actually accepted at ICSE 2020. And there's another paper that's called Manifold for Machine Learning Assurance, which is going to be presented in ICSE Near in a few days. So I combined all the materials and giving you an overview of the approaches that we are taking for the machine learning assurance and also for test generation. Okay, so everybody knows that machine learning is infiltrating into safety critical systems like Tesla's autonomous driving or Zipline. So for those who don't know, Zipline is a company that delivers medical supplies through autonomous drones. And they heavily rely on autonomous systems for the path planning and for perception of the objects on the way. And allegedly, they spend more than 50% of their time and money in verifying this system, like building the infrastructure for testing and testing the image classifiers themselves and gaining mileage and so on. So this is really a software engineering problem, and that's where most of the cost is being spent. So if you can do a better job in testing or assurance, it can be of tremendous benefit for the wider adoption of artificial intelligence and also for saving the cost. So there are assurance techniques for traditional software, like verification and for testing approaches, concepts, and so on. But not all of them apply directly to the autonomous system because of their data-driven nature. And also that it's not, I mean, the concept doesn't really translate, like what is a bug here? It's not something that we can take a look and logically fix, right? So then it seems like we are doomed to invent everything from bottom up. But I want to say that that's maybe not the case, and there are some big concepts that can be transplanted here and adapted easily. And that, I think, one of the biggest thing is model-based testing or model-based engineering in general. So model-driven engineering, this is a definition I brought from others' paper. It says that we can create a model and take advantage of it. Like these are conceptual models that explains the problem domain, and like it can be a behavior model, the input domain model, and so on. And we can make use of this abstract representation for activities, verification activities like test case generation, runtime monitoring, or for building assurance cases and so on. So what does this abstract representation look like for machine learning tests, and specifically for image classifiers? So I'll give an example. This is the depopular MNIST data set where there are 60,000 samples that look like this. If we are to build an abstract model manually for explaining this data set, it'll be like this, I think. Like the digit labels, we can think of the thickness of the digit, the shape, orientation, and so on. If you can use these latent variables that we can relate with and understand, then we might be able to explain the whole data set. And of course, that's not a trivial task given the complexity of, given the high dimension of the problem domain and the complexity of these data set. And that is for the simplest one of image classification. So we wonder, if you can obtain those models, it'll be very valuable. We can use it for testing adequacy measurement, because when we have those set of latent variables that can completely explain the data, then we can see whether the distribution matches between a test suite that we have and the distribution we have from the training data, right? You can even think of generating new test cases if we have the generated capability that can be related to this, this hidden variables. So we asked ourselves this question, can we obtain this abstract model for machine learning task? And our answer is yes, and that is coming from this technique called manifold learning. And before I explain manifold learning, what manifold means is it's a hypothesis that machine learning makes in the beginning. It says real world data is presented in high dimensional space, like the images reside in a very high dimensional space, but they actually concentrate in the vicinity of a manifold, which is a much lower topological space embedded in this high dimensional space. So what that means with an example is the MNIST digit, they are like 28 by 28 pixels, and each pixel can have so many values. But the space for the valid digits is actually very small. It's not like if you create digits randomly out of the pixel, it looks like any digit. It's not. So the valid digit is actually living in a very small dimension. That's what this manifold hypothesis say. And manifold learning technique tries to uncover this structure and analyze this manifold. So from these techniques, our take from software engineering perspective is that, okay, it is analogous to implementation independent model of the input domain. If we have this, we can harness it for various testing activities. And that idea will be presented in Manifold for Machine Learning Assurance, New Idea and Emerging Result paper. So to continue on, we took this variational autoencoder as a manifold learning technique. There are other techniques, but this one has a unique advantage. For example, it gives me the encoder function and a decoder function that maps the input data set to and from this manifold. So you can think of manifold as a small lower dimensional space and the structure where the real data is encoded. So I forced all the MNIST data set into 2 dimension here, and the color encoding represents the digit class. And here I didn't even impose the label. So it's not a supervised learning technique. It's totally unsupervised. And everything I say is that, okay, for the first loss term, I want to make the reconstruction, which is the encoder and the decoder, this X hat here, make the reconstruction as similar to the input as possible. And the second term says, I want to impose a known prior distribution on this manifold space, and I want the posterior distribution after learning to match this prior distribution. The reason why the second term is useful is because when we know the distribution of the data set in this small space, if we sample a new case or new input from this space, the distribution of the decoded samples will match the original training data samples. So what happens after we learn a 2-dimensional manifold for MNIST data set looks something like this. It's a smooth space where all the digits are represented in this 2D space. And if you keep moving that point along this 2D space, each latent code will correspond to a unique input sample. And that can be, we can even modify it to work with condition, meaning if I specify the condition or the class label upfront to the encoder and the decoder, then I can obtain a manifold that is conditioned with the class label. So the space has this smooth representation, but per each class label. So these 7, 6, 5, they are in the 2D space, but it changes depending on the condition I specified to the decoder. Okay, so this is what we consider as a technique for learning the domain model, and we are going to utilize it for various purposes. And the first thing I want to talk about is test adequacy measurement. So you can think of this manifold as an abstract representation of the input domain. So it's like we have a space where we can measure the adequacy of a test suite on. So this ball-shaped thing is the whole space for the training data. So for any test data that is given, we can measure how much of this manifold space is being covered by that training data. And how we do that is by, dividing this space into regions, and by n equals sample mass per each latent dimension, and we create a grid. And the reason why it doesn't look equally spaced is because we have imposed Gaussian as a prior distribution on x-axis and y-axis. So this smaller segment is actually containing the same density of the samples in other sections, supposedly. And for the coverage obligation, we are forcing the test suite to have at least 1 test case per each bin that is created by this grid division. So the finer we go with the n, the more test cases that we require, and the more fine-grained diversity we are requiring for a test suite to have. So we performed a preliminary experiment with this and with the MNIST and EMNIST as a test data set, this table shows the coverage achieved by the subsuite divided by the class label. So 0 means all the zeros in the EMNIST data set, 1, 2, and so on. So as you can see, this manifold combination coverage is achieving something from like 14 to 20% of 30% coverage, while other criteria like the popular neuron coverage or neuron boundary coverage isn't giving me a good differentiation between like totally different independent subsuites. So neuron coverage is about 73% regardless of the data that I provide, and neuron boundary coverage gives me a very low score for regardless of the data. And so we measure what is the correlation between the coverage obligation and the semantic feature that we are interested in. So we are hypothesizing that manifold coverage has a very good shows a very good correlation to the semantic feature. And since class label is one of the most obvious semantic feature, we measure the correlation. And the Kramer's fee correlation score that we got was as follows. Neuron coverage achieved 0.13, while manifold coverage achieved 0.83. So that's a high correlation. And I don't know what correlation with other popular criteria achieve. We didn't perform experiment for surprise adequacy here, but I imagine that surprise adequacy is a criterion that just measures the surprise, and it doesn't differentiate between the surprise of 1 or surprise of 7. So I guess it doesn't have a good correlation to the class label, but it doesn't mean that it's not valuable or anything. I think this manifold coverage has a unique advantage of associating with the semantic features so that we can use this coverage as a model-based coverage kind of thing. And we can use implementation-based coverage like neuron coverage or surprise adequacy as a structural coverage in the source code analogous to. Okay, so that was about the coverage measurement part, and this is the test generation part. As I mentioned, the key here is to generate test cases, not just input, but along with the label, because if we can only generate test inputs, we need to sit down and label those images, which is not so fun. So here we employ this conditional VAE for specifying the label up front and generate novel test cases. And also fault finding one, not just any case, but we attach this model under test right next to it so that maybe as we synthesize new test case, we can just quickly check whether the expected output matches the output of the model under test. And if it is not matching, that indicates it's a fault revealing input. So we add that to the test suite we collect. So for generating new test cases from this manifold, we could think of 2 different strategies. The first one is very simple. It's the default use case of the variational autoencoder. We can sample from the Gaussian prior that we impose during training. Then the output distribution would match something like the training data distribution. And the second approach is our take from software testing perspective. We can apply search on this latent space because instead of searching in the input space where it's very high dimensional and most of them are just irrelevant data, if we search from this manifold where all the inputs that are sampled from there are in distribution, we can obtain realistic, not like adversarial, but realistic fault revealing input. And we applied particle swarm optimization on this manifold space with our custom crafted optimization of the cost function. And one of the cost functions that we applied in the experiment is this. The first term, O1, is about here sigma is the Bayesian uncertainty of the model under test. So we can plug into the model under test directly and see what the uncertainty is. If the uncertainty is high, it's known to reveal more faults. So we are maximizing the uncertainty, and the graph looks something like this so that it doesn't go beyond infinitely, but the maximum value is 1 and the minimum value is 0. So we have that term. And another term is that since we have this Gaussian distribution as a prior, we don't want to drift too far away outside the manifold. So we are slightly modify this normal distribution function to account for that. And we combine these 2 terms for the final cost function. And I also want to mention that this paper that I guess a few hours ago, Professor Yu talked about this, the search-based image-based navigation. I saw that we were thinking in a pretty similar line of thought, and they contain some interesting experiments that we didn't perform. But our work is also has some unique characteristic in a way that they didn't solve the Oracle problem there. They just went with vanilla VAE, and we are using this conditional VAE. And also we tried on more high dimensional inputs and tested the feasibility of this technique for realistic image classification tasks. Okay, so this is what the reconstruction looks like. The upper row is the original data and the lower row is the reconstructed data. So this is to showcase the generative capability of the VAE itself. And you can see that for MNIST and Fashion MNIST, it's pretty faithful. And for TextNet, which is a data set provided by our industry partner, it's working pretty well as well. But for CIFAR, it's not. The images are blurry and weird because I think CIFAR 10 is a very tiny image data set and the complexity is very high. So VAE wasn't able to capture that as well. And this shows the generated image we just generated from the scratch from the manifold. We specify the label and just sample randomly from there. So each row is conditioned by a unique class label. So for TaxiNet, for example, the top row shows when the aircraft is on the right side of the runway, and the second row is on the slightly around the center, but on the right side still. The third row around the center, and so on. And as you can see, the conditioning works pretty well. It was able to generate images that are consistent with the label we provide and also look fairly realistic. So this is a result of the experiment that we performed for measuring how realistic the input data is. We measure the FID score, which is a popular score for measuring the capability of the generative models. And that FID score was pretty low, meaning that it was pretty close to the training data in terms of the diversity and how realistic the images look. And we compare the two approaches of random sampling or sampling from the Gaussian and the search-based technique. And interestingly, we could we could generate the same number of fault-finding inputs here, like 1,000, out of only 3,000 synthesized inputs. So with search-based technique, because we are looking at the signal from the model under test itself, with much fewer number of test cases, we are able to find the fault. But if you look at the time, interestingly, it's not very efficient because random sampling is so easy. It takes no time to optimize or anything. And also running it through the decoder for synthesizing an image is a very quick process. So although we had to generate lots of inputs, just checking it again and again is very cheap. So it took less time to find that. And one of the limitation was that we had to inspect the images manually to see if the synthesized test cases are actually sensible. I mean, it can be like, okay, the test generator will say it's 7, but it may actually look like 1 in some cases. So that is reflected in this column, the time we invested for checking the consistency of the label. So this is a one-slide summary of my talk. We believe that manifold enables model-based testing sort of in the machine learning domain. It enables an independent assessment of the model under test because the VAE is learning something regardless of the task that the model is performing. It's just learning to reconstruct the whole data set. And the model is performing the specific task of the classification or regression or something. So here, this picture shows that the manifold is only consuming the input, not the label, while the machine learning model is consuming both the input and the label for supervised learning tasks. So we can think of the lower as a specific implementation, while the upper as an abstract representation of the input domain dataset. And this independence allows to perform several interesting testing activities, such as the adequacy measurement, test case generation. And these are all possible activities that we can perform. So for the detail, please look at our AI test paper. And also I want to suggest this second paper called Model-Centered Assurance for Autonomous System. This is a paper from the SRI group, and they also talk about the idea of using model for the assurance task for this autonomous system. And I found that very interesting. So for the future work, we are still keeping up with this bunch of ideas here, and please read our paper. Thank you.
Thank you. Thanks a lot. So we have one question from Vincenzo Riccio. He asks, can the technique be applied to tasks different from image classification?
Yeah, very good question. So we are exploring that idea actually. So one of the things we are exploring is in the reinforcement learning or for sequence task. So with a sequence task, you can create the same VAE structure, but only with the LSTM or RNN for the encoder and the decoder. Then it is the same that we obtain a latent encoding, but the difference is that the latent encoding changes over time, and we need to keep track of that using some explicit model or something. So we are exploring the idea of expanding this for other types of tasks also.
Okay, I have one more. Okay, we have another question from Vincenzo Riccio, who asks what happens when the data set, I guess the training data set is of poor quality.
Well, the training, if that is the case, it'll only work as well as the training data set. And that is the same for the model that you're developing as well. Right?
Okay.
Yeah.
So there is one more question from Andreas Stockholm. An overly trained variational autoencoder can reconstruct well also some unseen images, given the features it has learned, if they're sufficient close to the distribution of the training data. How would you train a variational autoencoder so that it's good on in-distribution data and bad on out-of-distribution data?
So very good question. That's I don't have a good answer for that actually. So that is in one of the future work that we are planning to do, like understand more about the test cases synthesized from the manifold. If it is really like authentic or novel, or if it is just a interpolation between the training data. I think it is only as good as the training data. If we apply augmentation during the training of the variational autoencoder, then it would be able to extrapolate beyond the training data itself. But it wouldn't be able to generate all of a sudden some cloudy images when your training data is only sunny images, right? So that I think that is the limitation, and there might be some possible extension when combining with the metamorphic testing in that sense.
Okay, so I think we should move forward to the next speaker. Thanks a lot again for your presentation.
Thank you.
Thank you.
So our next talk is DeepFuzz generating models with deep learning to find bugs in the Simulink compiler. Sorry. So this work will be presented by Sohail Lal Shrestha. Simulink here is a development tool for cyber-physical systems, and Sohail will tell us about using the neural language model that will automatically learn validity rules from an existing corpus of models for the scenarios where complete specifications are not available. Please go ahead.
I guess you're muted.
Okay. Yeah.
Am I muted? Can you guys hear me?
Now, yes.
Yeah.
Now, yes.
Okay. Yes, sorry. Okay, let me start again. So yeah, my name is Sohail Shrestha, and today I'm going to present our work at DeepFuzz generating Simulink models with deep learning to find bugs in the Simulink toolchain. So when designing a complex cyber physical system, be it a vacuum cleaner you use in an apartment or a complex fuel management system in an airplane, engineers often design graphical block diagram models of the system using commercial CPS toolchains such as Simulink. Often these toolchains are used to automatically generate codes and executables that can be directly deployed to the target hardware. As these executables are often deployed in safety critical systems, it is important that we eliminate all the bugs in it, as a bug in the toolchain can propagate to the artifacts they produce. So in software engineering, there are a number of ways to approach the problem. Ideally, we can formally verify the entire Simulink toolchain, but unfortunately, this is not feasible due to its large code base. Also, we lack a complete formal specification, which can be partly attributed to its commercial nature. And this is further aggravated by the rapid release cycle of Simulink occurring twice every year, making it rather expensive to formally verify, even if the specification was available. So given the infeasibility of formal verification, previous state-of-the-art work like SLForge explored in the direction of randomized differential testing. So SLForge has two main components. The first component is a random Simulink model generator, which generates the Simulink models. And then these randomly generated models can be compiled or simulated in different compiler modes, both of which generates executables. And the generated executables are then executed on the same input. And then the tool observes its output to check if the results are the same. Any discrepancy in the output suggests that there is likely a bug in the compiler. So SLForge has proven effective and has established itself as a state-of-the-art random model generator, triggering 8 new confirmed bugs. However, the tool's random model generator component is guided by the freeform specification parsed from the Simulink's webpage. And it is able to encode a small subset of Simulink specification despite significant research and engineering investment. And the problem is further amplified by the need to manually update the tool whenever Simulink adds or changes its rules. And the engineering effort do not translate well to other tool chains as the tool is tightly coupled with Simulink. Therefore, the idea or the motivation behind our work is to automatically capture these rules without having to parse them from the web page using deep learning methods. And the other motivation, like our work is initially motivated by, is the work of DeepSmith. A quickly little summary of their work is contrary to using language specification for compiler fuzzing, they propose to learn from a corpus of real-world code and generate realistic programs. These generated samples are then used to do differential testing. So results show that they have found 50 plus bugs in various OpenCL compilers. Furthermore, they made the claim that the architecture is easily extensible to other programming languages as well. One thing to note here is, unlike OpenCL, Simulink does not have specification publicly available. Therefore, it makes more sense to use deep learning for Simulink model generation than OpenCL. Just to give you a quick idea of what language modeling is, the key definition of language modeling is task of predicting the next word in the sequence given a set of previous words. So due to time limitation, I won't go into details about how it works, but state-of-the-art language models typically use recurrent neural networks or its variant, long short-term memory networks, since they are able to capture long-term dependency in the sequential text. So therefore, in this work, our approach is to learn from a corpus of Simulink models directly using DeepSmith architecture. In doing so, we are able to validate the claim made by DeepSmith, as well as test our hypothesis that deep learning-based model generator can even capture the undocumented specifications. Quick little digression to show you how typical Simulink models look like. So the basic component of a Simulink model is a block, which can represent equations. The blocks have connections between them through which data flows. And Simulink by default supports many standard block libraries, which is similar to library in other programming languages. And to deal with increasing model size and complexity, blocks can be grouped together in a subsystem or a separate model, like the one you just see on the slide. So as we portray the random Simulink model generation as a language modeling problem, first we have to decide what will be our training corpus. So we cannot directly use the graphical model as it has to be encoded in a textual format. So for that, we had two choices: either to use the new SLX format of these Simulink models that separate different Simulink block components in separate XML files, the one you see on the slide, or to use the MDL file format, which is MathWorks' proprietary file format before 2012. So the main difference between these two being MDL file consists of all the necessary model parameter definition in a single text file, while SLX does not. So that is one of the reasons why we restricted ourselves in studying as well as only using MDL files in our training corpus. And since Simulink has support for converting MDL to SLX format, this is an added advantage. Also, we don't want to overburden our deep learning model to learn unnecessary rules that does not contribute to generating valid models. So we studied the MDL file and found that the model component designed by user in Simulink is defined under the system structure. And stripping all other structure apart from the system does not affect its validity. So these are the phases of DeepFuzz SL. As mentioned in the earlier slide, we only include MDL files that has that system structure in our seed training corpus and ensure that all models are valid. So a valid Simulink model in our case is models that can be opened and compiled by Simulink. Moving on, once we have our corpus ready, we add a basic pre-processing steps. In doing so, a simple model in a slide is transformed to a model with all blocks and lines stacked on top of each other. Rest assured that the semantic meaning of the Simulink block is intact and only the visual representation of it is changed. Next, as the neural network expects numeric sequences during our initial experiment, the trained neural net generates Simulink models with no connections. Upon investigating, we found that the MDL representation has all blocks definition first and the connections definition later, the one you see on the slide. So to mitigate this issue, we restructured the MDL representation to have a pair of blocks followed by their connections. So next, as neural networks expect numeric inputs, numeric sequences as inputs, we transform all of our seed models into a sequence of fixed size feature vector. So ideally, we want to compress the input text, keeping the number of tokens in the vocabulary low for our language model. So to understand how different encoding scheme affects the size of tokens in the vocabulary, we took 30 Simulink models and encode them using character and word level encodings. The results, as you see in the table, suggest that character level encoding in combination with some common pre-processing steps keeps the vocabulary size small, while word level encoding maintains the size of tokens. Hence, to limit the size of the resulting feature vector and the vocabulary, we encode them using a hybrid scheme that maps keywords to few common keywords to tokens and the rest to characters. We then train our neural network using the same architecture used by DeepSmith, that is a 2-layer LSTM network with 512 nodes per layer. The network is trained using Atom Optimizer and cross entropy loss for 400 epochs. So after the training is done, we sample from the trained neural network token by token, seeding it with a model and an opening curly braces keyword, as all Simulink models start with those keywords. And our stopping criteria for generation is when the curly braces are balanced or it has reached a maximum number of allowed tokens. So in our experiment, we use 5,000 as our maximum token count, corresponding to the maximum Simulink model size in the seed corpus. One more thing is we want to maximize the variation in the generated models. So to do that, choosing the next token with a maximum probability greedily is not a good idea, as we'll end up with a lot of same generated models. For example, if when seeding it with a model and opening curly braces token as a seed to the trained neural network, it might end up predicting block type as the maximum probability chance, And if we only keep on choosing that, we will end up with the same models, a lot of same models basically. So to address that issue, we perform a single multinomial experiment on this predicted probability distribution, which randomly picks a token based on the learned distribution. To introduce even more randomness, we modify the predicted probability distributions using 3 different sampling strategies before performing the multinomial experiment, the one I talked about in the previous slide. So first we try temperature sampling, which scales this predicted probability distribution using a hyperparameter called temperature. A low temperature makes the language model increasingly confident in its top choices, while an infinite temperature corresponds to random sampling or uniform sampling. The other 2 samplings are top P and top K, which are quite similar. In top K, we consider K highest probabilities, while in top P, we select highest probability tokens whose cumulative probability mass is greater than P. And lastly, we filter the generated models by opening and compiling them in Simulink. Coming to the experimental setup, we use TAC, which provides a high performance supercomputer. We trained our deep learning model on a TAC Maverick 2 GTX node with the following resources. And for our training data, we use SL4 generated models in this particular preliminary evaluation rather than using real world models, because for SL4 generated models, we can control the size and properties of the models, while third-party models are quite diverse and they are, so publicly available corpus are quite small in size for our deep learning model. And the training took about 2 hours to complete. So to evaluate if a DeepTest SL can generate valid Simulink models, we generated 1,024 samples using 3 different sampling strategies, each of which took about 13 minutes to complete. So regardless of the sampling strategy, DeepTest SL is able to consistently generate over 90% valid models. So moving on, our DeepTest SL generated models triggered 6 instances of Simulink crashes, 5 of which occurs when Simulink opens the generated models, and the other one while Simulink compiles the model after successfully opening it. So far, we report 2 issues as bugs to MathWorks. The first issue, which is a representation sample of the 5 crashes, is confirmed as a known bug in which Simulink parsers should have rejected the model. And the other bug is triggered by the model on a slide. It has 25 blocks and 12 connections between them. So MathWorks confirmed that this is likely a new bug, and the crash occurs due to a missing output port in a signal generator block. So this bug is particularly interesting for us as it validates our hypothesis that DeepTest SL generated Simulink models cannot be generated by SL4. It's mostly because SL4 calls API to generate the signal generator block, while we write the code in itself to construct this particular block. So in conclusion, DeepTest SL is the first work that used deep learning for random Simulink model generation to test Simulink toolchain. And we found 2 bugs in Simulink toolchain, and the prototype implementation as well as evaluation data are open sourced at GitHub. Lastly, I want to thank TAC, NSF, and MathWorks for providing resources and funding the research. Thank you.
Thank you. So we have one question from Carlo Alberto Furia. It says, if I understand correctly, you mentioned that Simulink models may have undefined behavior. How do you ensure that your generated models are free from undefined behavior?
So in this particular work, we do not have such constraint. So we just take all the models and try to learn whatever we can. So this is actually a part of a future work right now.
Okay, thank you. I have one question about the validity of models and of the bugs that you found. So if I understand correctly, you consider a model valid if Simulink compiles it without a crash.
Yes.
So how then do you find the bugs in Simulink? So you look into the ones that Simulink was not able to compile and see was it correct or not?
So right now, the bugs I have reported are the bugs in the Simulink parser.
Okay.
So it's actually constructing Simulink models that are possibly have undefined Simulink behavior. So that got like 5 crashes, and one was actually able to pass this initial Simulink parser and go to the compiler end, which should not have happened because this particular signal generator block I talk about in the last slide should not have passed from the Simulink parser in itself.
Okay, and one more question. So I wanted to ask what you have done, the approach, how much is it specific for Simulink? So if I want to apply a neural language model to test another type of application, should I start from the scratch or can I just somehow readapt your approach?
Yeah, this approach is actually very adaptable. I actually have a release in the repo that you can basically just put in your training corpus of whatever language you are trying to train and just train it without any input, like any kinds of engineering effort.
Okay, and one more question here is, does the approach generalize to other modeling formalisms?
So we haven't actually explored on that question. Possibly yes, but that might be a speculation at this point. So my answer would be it should generalize to other modeling formalism as well.
Okay, so I think we will go forward with the next talk. Thanks a lot for your presentation.
Thank you.
So our last talk of the session and of the workshop is, does neuron coverage matter for deep reinforcement learning, a preliminary study? The talk would be presented by Miller Trujillo, and as the title suggests, it will tell us whether the neuron coverage adequacy criteria performs well for reinforcement learning systems. So Miller, please go ahead.
Hi, I just sent the video because I'm having unstable connection. So can we go with the video, please?
Sure.
Oh, do you have the video or should I present the video?
Maybe you can share your screen and start the video. That would be useful.
Okay, let me just find it.
Trujillo from Universidad de los Andes at Colombia.
Well,
enable your screen sharing first, Mila.
Yes.
Great.
Yes, we see it. But if you increase the video size, that would be useful.
Fine?
Yeah.
That's fine.
Here it goes.
Hi all, I am Miller Trujillo from Universidad de los Andes at Colombia. This is a collaborative work with Mario Linares Vázquez, Camilo Escobar Velázquez, and Nicolás Cardoso from Universidad de los Andes, and Ivana Dusparik from Trinity College, Dublin. Our work is about neuron coverage as a testing metric for deep reinforcement learning. First, let's start talking about reinforcement learning. So the way it works is that there's an agent that perceives a state from an environment and performs an action that will change this state. Furthermore, the environment will give a reward signal based on the agent decisions. So what we want to do here is to learn to pick an action that maximizes that reward signal and a long-term reward. For this, we could just go further and explore the possible states and the possible results and learn what will happen based on this experience. Then we will take the best actions depending on the state and the experience. Actually, this is called a policy that is a function from states to actions. However, as you can imagine, as the environment gets complex, trying to learn how to pick an action gets harder. Here is when we can introduce neural networks. We can use them to approximate the policy, and this will be really useful as the state space or action space becomes too large. So deep reinforcement learning is simply using a deep neural network to work as a policy. But the problem using DNNs here is that we actually don't know if the DNN is approximating an optimal policy or even a good one. In contrast to supervised learning, here we don't have an explicit goal value. Our only metric is reward, but it won't tell us if our policy is optimal. And by now, there are no specific testing techniques for DLL systems. So the question is, how do we know that the output from the DNN is the expected one? If we ask this question using purely DNNs, there are some metrics that addresses. For instance, the neuron coverage that is an adaptation of a statement coverage when testing regular software. Actually, neuron coverage had been studied and proposed as a white box metric in some frameworks like DeepExplore. Moreover, there are some testing tools like DeepTest that empirically demonstrates that changes in neuron coverage are correlated with changes in the actions of self-driving cars. But does these traditional DNN testing techniques actually apply to DLL? That is our main question and motivation. But in this work, we focus only in neuron coverage. Therefore, our research questions were, is there any difference in the evolution patterns of neuron coverage for the different layers in a DeepLL system? And is there any correlation between neuron coverage and a cumulative reward in a DeepLL system? To address these questions, we designed an empirical study using the mountain car problem, which is a classic control problem where there is a truck stuck between two mountains and we want to climb the right side mountain. However, the engine of the truck is not strong enough, so it has to move back and forth to gain momentum and climb the mountain. So the goal is to climb the mountain, but there is a time limit that is 200 steps. The environment describes the steps using the position and the velocity of the truck, and the action that the agent can take are move towards left, move towards right, or simply do nothing. Also, the goal is described in terms of the position. So if the truck reaches a position greater or equal to 0.5, then we say that the truck has climbed the mountain, and we will give a positive reward in this state. Otherwise, the reward will be -1. Now, for solving the mountain car problem, we randomly select two models that use DQNs. The first model, model A, have 4 hidden layers, and the input layer use the current and the last state. The model B use the current state as an input and have 2 hidden layers. For both models, the output layer is the same as there are only 3 possible actions. It's important to note that in model A, the second layer is a flattened version of the first layer. That means that the neuron's activation values are the same between these layers. Now, for collecting the data, we train and test the models in sequences of iterations, episodes, and stages. So we start training, performing at most 200 iterations or actions per episode. If during a training episode, the truck climbs the mountain, then we perform 20 testing episodes. And this will happen 1,000 times as we use 1,000 training episodes. And also, we use 5 stages per model. Understanding and stage like this whole process of training and testing. These were the training parameters that we use for the models. And finally, these are the metrics that we use to address our research questions. The first one is neuron coverage, that is counting which neurons were activated for a specific input. The second one is neuron layer coverage, that is the same from neuron coverage, but only counting for a specific layer. These 2 metrics will help us to understand the relationship between coverage and reward. The third metric is cumulative neuron coverage, that is the total number of neurons that have been activated until a specific time step. And finally, the last metric is cumulative neuron layer coverage, that is the same from cumulative coverage, but again for a specific layer. These cumulative metrics will help us to address our research question about the evolution patterns. This is because these metrics take into account previous values, so we can evaluate evolution in a better way. Let's see at this example to better understand our metrics. So let's assume this network, the brain neurons mean that were activated at this step. So in the first iteration, we will have 5 neurons activated in the whole network. Therefore, the neuron coverage is 5 out of 12. And if we take a look to a specific layer, for example, first layer, L1, there were 2 neurons activated. So NLC for this layer is 2 out of 5. As there is no previous iterations, in this case, the cumulative metrics have the same values for the non-cumulative. For the second iteration, there is again 5 neurons activated in the whole network. Thus, the neuron coverage is 5 out of 12. However, there are 3 neurons that are active now that were not active in the previous iteration. Therefore, the cumulative neuron coverage is 8 out of 12 at this moment. For the layer level, happens the same. So even though for the first layer there are only 2 neurons active, the cumulative version will come up to 3. Now, after performing the experiments and computing the metrics, we can start talking about the evolution of coverage for model A. So these plots show the distribution of CNC and CNLC over training and testing in model A. During training, for CNC, on average, 95% of the neurons were activated, and all the layers were able to execute all of their neurons, that is CNLC. Another interesting thing here is that the output layer of the model A report the lower average 80% from the 2 models, showing that having less neurons does not necessarily result in higher cumulative coverage. Now, going to the testing results, we can observe that there is a reduction in the cumulative coverage in the layer and network level. More concretely, the reduction was 45% on the average CNC and 42% on the average CNLC. Finally, during testing, 42% of the episodes succeeded climbing the mountain. There is a success rate of 42%. Now, this plot shows neuron coverage and neuron layer coverage per episode for training in model A. Note that for visualization purposes, we only present 3 out of the total 5 stages. Well, now we can observe that neuron coverage behavior for the output layer is erratic across the different stages. Also, for the first 2% stages, the first layer shows higher coverage than the following layers. However, the third stage flips such behavior. Again, remember that the second layer is a flattened version of the first layer. So there is an exact mapping between these 2 layers, and that's the reason because the second layer is not showing in these plots. Now, let's look at the reward. These plots show the cumulative reward per episode. At a first look, the behavior of the signal seems erratic, especially because the best rewards are not necessarily reached at the final episodes. But if we take a better look, we can also observe that these reward signals look quite similar to the coverage signals of the last layer, at least for this model. In contrast to model A, model B shows lower average CNC with an 86%, and only the first and the last layer were able to activate all of their neurons. For model B, the reduction on testing was 30% on average CNC and 25% on average CNLC. Finally, this model got a 77% success rate. Look that even though model A have better cumulative coverage during training, its success rate and cumulative coverage in testing are lower compared to model B results. For this plot, the behavior is similar to the one described at model A. The last layer is erratic and the first layer shows higher coverage than the following layers. And also, looking at the cumulative reward, we can observe that the signals look similar to the coverage signals at the last layer for this model too. After noticing this behavior, we decide to compute Pearson and Spearman correlations to evaluate this. However, the result was negative or lack of correlation. Now, given our results, we found that better coverage in training does not necessarily mean better coverage in testing. Also, that training and testing evolution patterns are not necessarily the same. And because of the negative and lack of correlation between coverage and reward, we think that neuron coverage is not sufficient to reach substantial conclusions about deep RL systems. Finally, as future work, we think that neuron coverage as a testing metric should be extended to other deep RL scenarios, like other classic control problems, to consolidate the validity of our results. And also, similar approaches could be used to evaluate other DNN-based models. Before closing the presentation, I would like to make a quick summary. As said before, our goal is to see if traditional DNN testing techniques apply to DRL, and we focus in neuron coverage. This is to present a first step towards testing of DRL systems. In this case, we try to answer these two questions. The first one about evolution patterns of neuron coverage, and the second one about correlation between neuron coverage and cumulative reward. For addressing the previous questions, we conduct an empirical study using a classic control problem, mountain car, and randomly select two models from GitHub that solve it. We also define these four metrics based on neuron coverage and cumulative neuron coverage, which have network and layer level. And finally, we obtain some important insights like better coverage in training does not necessarily mean better coverage in testing. Also, that the evolution patterns are not the same between training and testing. And because we cannot find any correlation between coverage and reward, we think that neuron coverage is not a sufficient metric to reach substantial conclusions about DRL networks. Thank you everyone for your time and your attention.
Thanks a lot, Miller, for anticipating the connection problems and preparing the video. So we have two questions in the chat now. One is by Vincenzo Riccio. He says that neuron coverage evaluates the adequacy of a test suite. What is a test suite in this reinforcement learning context?
Okay, I think that that is the question that we want to address in this study. And as we said in the presentation, we didn't find any correlation between the coverage and the reward. So we don't think that neuron coverage is is not sufficient to have enough conclusions about RL systems. I think that is what is the test would be.
Okay, so moving on to the next question by Andrea Stocco. He says, as far as I know, very few inputs are necessary to stimulate most neurons in a DNN, which is quite true also in your setting. The output space of the DNN is only 3 actions. Suppose that the adopted policy favors only one kind of action, exploitation. It's unlikely that exploration of the output space and implicitly of the network would be high. What is your opinion on that?
Okay, I will read again the question on the chat.
Yeah, go ahead.
Briefly, so we start stimulation. Yeah, space road. Only one kind of action. Okay. It isn't like exploration of the outer space will be high. Well, the first step when using DRL is that you have the exploration, which is kind of random step. So if you go through exploitation, I think that is because you are not using a good exploration policy. So in our setting, we actually have enough exploration. As we said, we use greedy exploration policy, and the epsilon value was pretty high at the first steps. So the exploration was quite high, and we did not find any problems with exploitation. Exploitation. So that's what I.
Okay, thank you. And I have one more question. I wanted to ask, what is the motivation behind the cumulative neuron coverage metric, or the layered version of it? What does this metric tell us?
Okay, because we were concerned about the evolution without that maybe a cumulative metric that will count like previous iterations will be a better fit to understand the evolution of some metrics. So it's like quite related with evolution as we count for previous iterations. So that's the motivation of cumulative neuron coverage. Also, we did not present these results in the paper, but we also calculate the correlation between neuron coverage, cumulative neuron coverage with reward, as both metrics were cumulative. But again, we did not find any correlation in those metrics. So the main motivation behind these cumulative metrics were the evolution, but we also try to evaluate for the other research questions.
Okay, thank you. So I think this concludes the presentations. We will take a short 2-minute break, and then Karina will take over with the panel.
Okay.
See you soon.
Okay, thank you. I would like to share my screen. Can you hear me?
Yes, Corina, we're having a couple of minutes break for the
I was
attendants to
thinking,
stretch their legs and stuff.
I was thinking to share my screen. So I'm using my phone for audio, but the computer for sharing the screen. So I can share the screen, and wanted to share the web page basically. Just to, let me see, share. Can you see my screen?
Yes.
Yes.
Yeah. Okay. I mean, I just wanted to
Set up. Yes.
Set up and the audience to have the panel participants in front of them. I hope all of them are online. Let
I had
me
a
check.
look 5 minutes ago. They all appear online. There is Ali. Yes. Carlo Alberto is there.
I think they are.
Okay. And a quick
And
question about the logistics. So will we let people ask questions, or do you want me to read from chat?
I think it's better that you lead and you ask, feel free to ask any questions of yours, of course, and we'll catch and fetch questions from the chat.
Okay. So who will read the questions from the chat? Do you want me to read them, or
Yes,
somebody?
please. I think it would create less noise.
Overlapping, yeah.
Okay, now I'm trying to see, how do I see the chat? Okay. Okay. And we also have a lot of questions from the audience. And another thing is that we are a bit behind schedule, but I was thinking to still end at the prescribed time, because people might, including myself, might have constraints. So yeah, I hope you are fine with that. So, I mean, we'll see how it goes, but I don't think we should run for an hour. What do you think?
It depends on how it goes. It could be less or more if it's.
Yeah, but we
people
are
got engaged or
basically
not.
30 minutes late, so
Mhm.
I'm not sure we should make them. But anyway, okay. So let me know when we should start, please.
I guess we are ready.
Okay, great.
When Gunnar is there.
So we can start?
Yes.
Okay, hello everybody. It is my pleasure to moderate the second panel of the workshop. My name is Corina Păsăreanu, and you can see information about myself on my webpage. And we have 4 great panelists today. Carlo Furia, Matt Fredriksson, who also gave an invited talk earlier today, Ali Mesva, and also Zico Coulter. And you can see information about them on the website, but on the workshop website. But I would like to start by asking them to introduce themselves and tell us a bit about their interests. And I don't know if you want to enable video, it would be great so we can actually see you. So perhaps we can start with Carlo.
Sure. Hi, everyone. I'm Carlos. So my research interests are mainly in verification and formal program analysis, not very much in the context of neural networks or machine learning. So I'm a little bit of an outsider in this sense, in this workshop. But another research interest that I developed more recently is about applying Bayesian statistics for essentially data analysis in the context of empirical software engineering, and this has certainly some connections to at least the basic techniques, even though it's still different look as those that are treated in this workshop.
Okay, thank you very much. So Matt, can you please say a few words about yourself? You, the audience may already know you from your invited talk, but maybe some people join late. So please tell us a bit about your work, also in a broader sense related to verification.
Yeah, so I'm Matt Fredrickson, assistant professor at CMU. And my sort of main background is, or a lot of the work I've done is in security and privacy, and how that manifests in applications that make use of machine learning. And I'm a big sort of proponent of like more rigorous verification-based approaches to solving some of those problems. So like been talking to some of the other panelists like Karina and Zico about verification-based approaches for dealing with robustness. In the past have explored, like when it comes to privacy, verifying notions like differential privacy and figuring out how to sort of apply them in various settings in a way that's kind of customized to the needs of the application and will be most effective there.
Okay, great, thank you. And Ali, could you please tell us a few words about yourself?
Yes, yeah, so I'm a professor at UBC, Vancouver, Canada. My area is mainly in software testing, software analysis, test generation. And in the past, I think it's been 2 years that I've become interested in using machine learning mainly for automated program repair. So what are the best ways to basically represent programs, software programs, in a way that the machine learning engine can understand and extract features and patterns basically from the bugs and the fixes that we give them as input. So that's basically been what I've been focusing on. I haven't done any testing of machine learning, as this seems to be the theme of this workshop. But we've been mainly a user of machine learning for software engineering tasks, basically.
Thank you. And Zico, would you like to say a few words about yourself?
Hi, everyone. I'm Zico Coulter. I'm also faculty at CMU. And my work really focuses on machine learning. And so I do a lot of work in several different areas of machine learning and optimization. But I guess the most relevant to here is the work I do on provably robust deep learning, which essentially just means training both verification and ideally tractable verification of deep learning systems, as well as trying to use these verification procedures to train networks in a way that makes them certifiably robust to certain perturbations.
Okay, great, thank you. And we would hope this panel is a free discussion. So we would like to find out your thoughts about the presentations of the workshop and the invited talks, and then more generally the directions the community should follow. But we also prepared a set of concrete questions, and we hope the audience will also post questions at any time on chat, and I will read them to the audience. So we have the questions on the screen. So shall we start by me asking these questions, and then the panelists can take turns to answer, or just comment if you feel that the question is relevant to you. And also please feel free to also ask yourselves questions, and also tell us if you perhaps have some gaps in, we didn't cover well all the topics. So I will start with the first question. So in your view, how is testing and verification from the software engineering community, and I would say also from the CAV or programming languages communities? So how is, in some sense, traditional testing and verification compared to testing and verification from an ML perspective? And to be more precise, I guess here we would like to find out how about techniques that are applied to machine learning algorithm, testing and verification techniques applied to machine learning algorithms, but also using machine learning to improve testing and verification, if you wish to comment. So who would like to start?
I can give it a go.
Yes.
So that's an interesting question. So I think at least two different answers. One is that so I think the differences between the, let's say, traditional view of testing and verification techniques and the one that is relevant for machine learning are mostly really technical about essentially the problem domain. So I can take, for example, traditionally in verification, there is an emphasis on verifying, for example, functional correctness, proving other properties like termination and so on. And these properties maybe are not so relevant, or maybe they cannot be applied in exactly the same, defined in the very same way for machine learning systems. But I think these kind of differences are not really fundamental, in the sense that also the applications of verifications in communities like the software engineering and verification and programming language communities is not monolithic. So over the years, especially in the last decades, there's been a lot of differentiation, a lot of experimentation with applying traditional techniques to different kinds of property and different kinds of concepts, different domains, and so on. Another instead point of view that I think perhaps is a little bit more interesting, more relevant, is that I think when we talk about applying techniques like testing and verification to machine learning or neural networks more specifically, it seems, and I think this is has also been shown to some extent by the talks that we had at the workshop today, there are actually different aspects or different models that can really be tested, and these differences sometimes left implicit. So I can think in particular at least of two different, let's say, points of view. One is when we are testing, for example, or verifying the, let's say, the model definition. So we have, for example, a description of a neural network, and then we can think about, in the context of testing, can think about generating inputs in a way that they affect the training of the network in a certain way. So, for example, it might highlight lack of robustness and stuff like that. So this is the first level, so the level of essentially affecting training or model definition. Then once we have a fitted model, then we can think about using that as a black box, as like a predictor or a classifier. And then testing in this case, in this context, primarily means to generate inputs that, for example, check the prediction capabilities of the fitted model, or other features. For example, in the keynote a few hours ago, we had the example of fairness. So that's also another context. So these are the two levels that are they're related, of course, but they're different. And I think we see different works that have the target one or the other, or perhaps a combination. And I think I think it's an important dimension to realize that it's relevant. But then I can also think of a third context that perhaps is de-emphasized, because it's kind of like the most straightforward way of applying verification techniques in this context, which is essentially, well, so a neural network model, for example, it's still a program, it's still a piece of code. So it's like a Python code with that uses some libraries and so on. And so we could just say, okay, let's analyze it as if it were any Python piece of code, right? And generate tests for that and so on. This, of course, is probably not particularly interesting in the sense that it might not be so different than testing any other kind of program in the same programming language. But there might still be, I think, interesting peculiarities that, for example, we've seen some work about classifying bugs in neural network programs. And so it's possible that some of the bugs, just by being in these kind of programs, are more frequent or less frequent than the bugs that we find in, let's say, general purpose programs. And so, so I think, to sum up, I think there's a lot of transfer, natural transfer of the ideas of testing and verification from the traditional areas to machine learning. But I think it's also important to highlight exactly which angle we're taking on this.
I would like to chime in on that, because I think it actually raises an important point, which is that what the functional form that we expect of a neural network is kind of different from traditional programs. And that when people think about correctness of a neural network or some machine learning system, they don't think of correctness in terms of performing the matrix multiplies correctly or correctly applying a sigmoid operator. We intuitively think of correctness meaning that the thing will work in the environment it's put into, meaning that if I have a pedestrian detector, when I run it on streets, it'll find all the pedestrians. And the problem with this is actually, as far as we're concerned, impossible to verify, right? And so even the verification work we do with neural networks is typically talking about training performance, verifying that on the training set or on given known examples, the network is somehow stable to small perturbations in some manifold, right? That's sort of what we mean by robustness. But this is actually kind of clashes, unfortunately, with the typical notion of robustness people kind of want to have in neural network systems, which is to say we want it to work well, kind of in the same situations that humans work well in, right? So if it starts raining, these things shouldn't break. If it starts doing these things that shouldn't break, it should be able to detect a pedestrian. If the image is, if pedestrian is two pixels over to the left, which is a huge perturbation in pixel space, it should still work. And so I think that something to keep in mind with all these systems is that there's the big challenge in machine learning systems is there's no formal specification of all the inputs something should work on. We can't enumerate all possible images of pedestrians that we'd ever want to see. And so this makes the challenge of real verification, sort of the ideal verification, in some sense impossible. And it's going to always be impossible. What is possible is a very limited form where you say, okay, given this data and these possible transformations, is the system in fact robust to this, which gives us, which just like machine learning, we kind of trust its generalization capabilities. We sort of similarly put trust in these generalization of the robustness in these scenarios. But it does mean that we're talking about a very fundamentally different thing, I believe, when it comes to even when we say verification of neural network systems. This is very different from truly verifying that the system is correct. It's going to work as intended. And I think understanding that distinction and also, frankly, better advertising the distinction, because I think these things are often muddled in sort of popular terminology, is very important to the field. This is not a domain where you can ever get, because we're talking about open world performance, you really can't verify these things in the sense that we normally think about it. And so I think this is an important distinction that needs to be addressed in these two different areas.
So I want to refine that a little bit, though, Zico, because I think, look, I agree with you, but I think what you're referring to is more a function of, what we choose to apply neural network or machine learning.
That's actually incredibly true. Yes, absolutely.
Like we apply them in situations where the tasks are a bit more perceptual, right? We don't really know how to code up a program to do this perception task for us. right? And therefore, like sort of by automatic corollary, we don't know how to specify what the right behavior of that perceptual module is.
And I guess I would only say to that this seems to be the domain where machine learning is best suited, right? Because that's in some sense the point of machine learning is you apply to domains where you can't specify the input-output mapping you want. And so you have to rely in some sense on example-driven programming, which is sort of what machine learning is at a high level, right? But you're absolutely right that there are other circumstances, maybe more in sort of small scale control and things like this, where you can take a neural network based controller for some microcontroller for some car in some sort of automotive application, and actually verify that in the formal sense that we're sort of used to in terms of sort of as a control system. It's just that we typically use or not typically. I completely agree. It's a function of how we use machine learning, which is often precisely in these scenarios where we cannot give formal descriptions of the domain that make it so problematic to talk about verification of machine learning.
But so in a point that I'd be curious to hear other people's perspective on that I think is kind of started to emerge in some recent papers that has really kind of captured my imagination is, okay, so like with like norm-bounded robustness, right? Say we apply adversarial training, with L infinity norm, that is some threshold that like is reasonable. We can actually get decent performance, but like we full well know that that's not going to be totally adequate at capturing all the threats that matter when we deploy this system, right? Some sort of recent results suggest that like even though that's not the specification that the problem domain calls for, there's no perfect alignment between that and some like convincing threat model. The models that you get out of that seem to sort of, okay, so like they're going to be more robust in that sense, but for example, out of Maudry's group and some others, also seem to sort of have more interpretable use of the low-level features that they're trained on, and so forth. And so I wonder if like there are other cases, or if there's something larger here where like finding a good sort of partial formal specification that doesn't quite capture everything we need, can lead to sort of virtuous unintended consequences that do make models that are actually more resilient in the threat models that we care about, or the sort of scenarios that we care about, and whether there's any way to validate or test or verify that outcome, right?
So I think there's very well. So not to hijack. I'll this will be the last comment. Hijacking things too much. There's very mixed evidence on that point. I would actually say there's some positive examples like the papers from Alex Monti's group showing that these models, robust models, are useful for other things. You can use, they give meaningful image gradients. But there's also some work, for example, by Ludwig Schmidt and Ben Recht, as well as some others who I'm now forgetting their names. But and what they did is they recreated the process by which we generate examples for ImageNet. So they created a new ImageNet test set and tried to evaluate how well all these classifiers we've been working on generalized to this new ImageNet test set. And what they found is they all sort of, surprisingly, the order doesn't change too much. So better models are still better, but there is a sizable gap, sizable drop across all classifiers in performance. And that gap remains exactly the same for robust models. So to be clear, they tried to recreate ImageNet as closely as possible, still found a 5% drop. Due to some domain shift that we can't really characterize about what people are like now versus when they created ImageNet. And then we are unable to improve that at all with robust models. You see the exact same gap. So it's not even robust to imperceptible domain shift that we get from 10 years worth of Amazon Turk changes in people's mindset of Amazon Turk. Whatever those are, we can't characterize what those things are, but they must exist somewhere. So the point of this is I think there's actually very mixed evidence about what, so I agree with you that I think that robustness in some sense almost has to imply better robustness sort of in practice. But I actually am suspicious about the ability of L infinity balls or L2 balls to really perform well under that metric. And I think that that's actually a mistake people often make, is thinking those robustness models will do that, when actually I think those measures are very important, but almost more so as sort of understanding the underlying nature of classifiers, rather than as a real metric towards kind of robustness as we typically think about it.
Okay, thank you. Very interesting. So Ali, would you also like to comment? Hello, we cannot hear you.
Yeah, sorry, I was trying to unmute myself. Yeah, so I can maybe use an example from software engineering, right? So for example, in software engineering, we're using machine learning for different tasks like code completion and fixing bugs and so forth. And all of these models that we train, they're kind of fuzzy. There is no notion of like correctness in the sense that they always give us the right answer, right? And I think this is probably true in any domain in which you provide a lot of examples and you expect the architecture, the deep learning architecture, to learn some sort of patterns. And then in the future, when you give it something that it hasn't seen before, it tries to come up with a solution, right? So, and that solution, trying to verify that it's always the correct one is really challenging. And that kind of goes beyond what we've been dealing with in the past, I don't know, maybe 40 years in software verification, software testing, because in software testing, we always expect that there is a correct answer, right? So you give it an input and there's a correct answer that is possible. And we always look for kind of finding counter examples that will tell us that the system is incorrectly implemented. Whereas in these trained models, there is no notion of really correctness. There's this fuzzy notion of correctness, and sometimes it's close to what we expect, but not exactly 100%, right? So even like just to give an example, in again generating, let's say, fixes for faulty programs, the model can give you like 10 suggestions, and maybe from the 10, only one is what the developer would write. But maybe 2 or 3 are kind of close in the proximity of what potentially might, solve the problem, right? So how do you verify this? It's extremely difficult. So personally, I don't know what the solution is, and I don't know whether software verification or testing is the solution going forward, because we're dealing with a totally different beast here. It's a different type of system that we is kind of new to us, and we don't really understand it yet. That's my understanding so far.
Thank you. So I also wanted in some sense to give my opinion and to summarize the discussion. So it seems to me that there is a tension and also a temptation to, so let's say neural networks, or in general machine systems that use machine learning, they can be seen as imperative programs. So it's very tempting to apply existing techniques. And it's often in some ways much simpler, because these neural networks don't have pointers, don't have multi-threading. So it seems an easier problem, and actually that's why a lot of people try to apply existing techniques, and maybe coverage makes sense, and try to borrow from all this work, because it's very tempting, and ultimately they are imperative programs that people use, they run to get answers. But on the other hand, they have some particularities. This application might be dangerous because of what Zico also pointed out. You don't have precise specifications. And the fact that the systems are approximate, that could still be fine. Maybe you can come up with probabilistic specifications, but ultimately you might not have some. I mean, in some sense, what is a good specification for a classifier that recognizes cats? Or it's very hard to, so there is this tension, so we don't really. And another difference from, let's say, neural networks and imperative programs is this huge states. We have huge state spaces. So again, let's say you get coverage, people try to obtain coverage of the input space in the classical sense. You cannot really achieve that for an object detector in an autonomous car. How do you make sure you covered all the possible scenes that a car can encounter? So again, this is in some sense a particular challenge that people have not thought about in the traditional verification and testing world. On the other hand, people do want to use this kind of systems and in, let's say, autonomy or medical diagnosis, where you do need certification and you do need to relate at least the behavior of these modules to some high-level precise requirements, because otherwise nobody will allow you to drive the car, to use the car on the roads, or let's say to have robots that use it and so on. So perhaps, and this will lead to other questions here, perhaps one should relay these fuzzy objects to more precise system level requirements, and maybe the runtime monitoring also plays a role. So this is how to reconcile the two words. In some sense, we have these fuzzy objects that don't have precise specifications, or people expect them to work most of the time, but then you want to plug them into higher level systems that have precise specifications. I don't know how this can be reconciled, but would you agree with such a summary? So would you like to comment more, or shall we look at other questions?
Well, so I definitely agree that, like, you know, the challenges that people have been looking at in traditional verification and program analysis and bug finding and so forth for like 3 decades are completely are by and large irrelevant to the challenges that you face with, like, you know, verifying or bug finding in a machine learning model, right? As you said, you don't have pointers, you don't have loops or recursion, anything like that typically. What you have is a really large, you know, in the case of neural networks or random forest or something, but mostly sort of uniform and boring program with a lot of data sort of stored in the program itself, and techniques that help you sort of tease out, you know, complex kinds of control flow and points to relationships and so forth, just like don't tell you what you need to know in order to make any progress. And when it comes to, like, you're talking about sort of exhaustive testing, like even if you could enumerate like every image of a cat or every road scene or something, you wouldn't have ground truth for that. Like, so it's not, even if you could search over the entire space, what are you actually checking for in that search, right? That's precisely why you train the model to begin with. Back to sort of Zico's point about, like, there's no way to ever really formally verify these. So I don't know. I feel like efforts to formally verify machine learning components make sense when there's a good sort of well-motivated partial definition of correctness, like fairness or some privacy definition, or you know, if you're in a situation where like local robustness is a sensible thing to use, then that makes a lot of sense. But like full functional correctness or you know, any sort of like top level specification of what it means for this model to like do what it ought to, you know, just doesn't make sense. And it sounds like we're all kind of in agreement about that, right?
Okay, thank you. So I would like now, perhaps we can jump to another question, which is what properties other than robustness can be formally verified? And I guess we already heard about fairness and finding bias and so on. And in some sense, they are general properties. So the question can be nuanced and ask, can one really verify domain-specific, requirements? And then again, there is a tension, as Zico mentioned, that actually, if you would have had domain-specific requirements, you wouldn't need to use machine learning. You can write a better optimized program that implements them. So yeah, I would like for you to comment more on that, please. Carlo, would you like to talk?
So, if I understand correctly your point, so you're asking about domain-specific properties that could be verified. I imagine that I mean, it's true that we have this fundamental problem that it's very hard to have like a complete specification of expected behavior. But I can imagine something like a partial property, like if you want some sort of well-formedness property that is also domain specific. I mean, now I'm making up some examples that are silly, but just give you the flavor of what I have in mind. So, for example, for if we are talking about machine learning approach to classify images in some way, then I can imagine that there might be some kind of properties that say that, for example, the classification mapping should be invariant under certain transformation of the image, for example. You could rotate it or you could shift the colors in a certain way and so on, and expect that if the goal is to identify, for example, a certain type of object or animal or person, then of course this should not matter. And so this is the domain specific, it's still fairly generic. And so I can imagine other properties of these kinds are possible.
So who else would like to comment?
One simple property, which I think is again comes from the control setting, is stability of systems, right? So we actually can, from a dynamical systems perspective, you can verify even very complex systems to be stable if you set them up in the right way. So, I mean, the conditions by which you can guarantee things like the Lyapunov stability are very well understood. They've been sort of understood for 30 years, but have, or probably more than that, I think since the 60s, right? But have not been applied very much in the context of machine learning and neural networks in particular, but they are properties you can verify. And so again, it's a little less domain specific and more sort of a general property, but there are systems for which you can verify that, you know, repeated application of a function will drive it to zero and not blow up. And that can be very useful when modeling certain systems.
Yeah, please.
I'm sorry. I was going to say, and when you first said stability, I wasn't sure what you were referring to. It sounds like you are talking about some sort of like iterative stability of the model itself.
Dynamical system stability, exactly. Yeah.
I mean, so stability is really important for like privacy and in the training process. So one thing that I guess maybe we haven't really been talking as much about is verifying aspects of the model creation or the training process, which I think is like maybe a little bit more ripe for you know, specifying what the correct outcomes are and maybe has, you know, a richer space of partial properties that make sense and can be verified. But the flip side is, unlike, you know, the model itself, which is kind of a simple regular program, the training loop is probably not, and might require some more, you know, some heavier lifting and bigger machinery to get anywhere with it.
Yeah, I think verifying training is incredibly hard, especially since convolutions on GPUs are non-deterministic. Actually, they will get different results in floating point precision when you run them multiple times.
Not TensorFlow. TensorFlow 2 is doing a fantastic job controlling this. Actually, if you turn,
you can turn it, but it then makes it slower, right? So no one turns that on because it's then slower.
I do, because it drives me nuts if I don't have it on.
So no, I think saying anything about the training procedure, now maybe you are actually back to more traditional verification where we just do a very bad job of it, but it could be verified. But we typically don't, because we sacrifice everything for speed, and that's not always the best way to build verifiable programs.
So there is another question that, sorry, would anybody else would like to comment on this question, or can we move on to another one? So I wanted to also ask, which is related to the previous two questions. So what is different also from traditional verification and testing is that these systems are driven by data. And perhaps less studied is the topic of verification of the data itself. And Matt did touch upon this, because you can analyze the data to find bias, perhaps. But in general, I feel there are many questions that need to be answered, and perhaps the software engineering community can help. So how do we know when we have enough data, or what happens if there is poison data, or simply unreliable labeling? So what do people do right now, and how can we help? Maybe simple things would help. I mean, and again, what can we borrow from, maybe from the software engineering community to help with this? So any ideas?
Yeah, so maybe I can make a quick comment, because I have to leave soon to go to another meeting. But so one thing that is emerging within the software engineering community is the idea of, and I don't know whether this is actually originally from software engineering, but the idea of synthesizing data, right? So I'm sure this is also has happened in other communities, but we're seeing in software engineering more and more data that is being synthesized, because in some domains it's so difficult to actually get the data that you need, or enough of it, right? So for example, again, I'm using this program repair example again and again, but for example, if you're working in a domain, in a specific programming language, that there's not a lot of data out there in the public domain, and you don't have access to what Google has or what Facebook has. What people are doing is, for example, using mutation testing to mutate the program. So you go from the current version, which is supposed to be correct, you mutate it so that it's actually incorrect. And then you use the mutation version as the incorrect version, and then you go forward to the previous version, which is the correct one, right? So, and then you feed these two into the model to kind of teach it to learn the correct one given the mutation one. So basically being able to kind of synthesize data in this way allows us to kind of, maybe mitigate some of the limitations that we have in accessing actual real data from developers. Now, going back to the question of how much data is needed and how do we know whether we have enough data, I guess this is kind of, again, different from what we are used to, because for example, source code, we have the notion of coverage. So when you get like 100% statement coverage or branch coverage or path coverage, then you have a good feeling that at least you're covering some of the aspects of your program. Here, we don't really know. Like, is 10,000 enough? Is 1 million data points enough in your data set? Who knows, right? So, of course, you can always measure the accuracy of your model's output to some extent using some test data. But whether there is a upper bound and you've reached that or not is always up for debate. And there's so many different parameters that you can configure and play with. It's actually it's amazing, right? I mean, just think of the hyperparameters, or the different models, architectures that you can use, or the different features that you can provide in your data set. And any variation there could result in a different model and a different output. So yeah.
Yeah, also I think the problem of assessing let's say the quality of the data, if it's enough, if it has bias and so on, it's not. I don't think it's something that can be evaluated in isolation, because of course one of the key features of having a machine learning algorithm, or applying a machine learning algorithm, is that it should precisely generalize from data. So then I think it only makes sense to think of these properties of the data as trade-offs, the different possible trade-offs that can be achieved in connection with the different choice of models and fitting algorithms and so on that may achieve different properties in terms of generalization and so on.
So I wanted to make a quick comment that actually in the ML community, people do generate data. So GANs and different generative models are used everywhere. So just that they do it differently from the software engineering community. So yeah, anyway. So any more comment?
I mean, so like another thought about you know, what things from the software engineering, you know, community, either research or the sort of more applied side of things could benefit machine learning. And one thing that strikes me, and this relates to the way that like data, you know, is brought in and evolves over time and is related to various models, is versioning, right? So like maintaining sort of coherent ordering as a model and a data set and a validation set and so forth evolve over time, I think is just as challenging, if not more challenging, when you're working with machine learning as it is with the traditional software project. And at least to my knowledge, there aren't great solutions out there to sort of help people manage that. And this certainly leads to issues like reproducibility problems and possibly reliability and so forth issues down the line when people sort of get sloppy with how they keep track of these things as they go along. So that seems like one area that software engineering has made wonderful contributions to, you know, computer science and engineering over the years, and you know, we're waiting for something like that in machine learning as well.
I totally agree, but I also think that perhaps these kind of challenges are not are even a bit more general than just machine learning. I would say that even, for example, it's like scientific computing in general may suffer from some of the same challenges, because they also write programs, they also write code, but they write code that is unusual. So it's not like the code that software engineering is used to analyzing. And so, and they badly need the practices that are standard in more established areas where let's say software engineering has been more prominent.
Yeah, absolutely. That's a good point.
Okay, great. So we are running out of time a bit. So Andrea put 2 questions on chat. So would you like to read them, please? Andrea?
Yes. Sorry, I had to unmute myself. So yeah, it was like more, I guess, perspective question. Like, so what are the tasks that you envision, which like, you know, you see more challenges to be tackled for us, other than, you know, the ones that are really popular right now? It's just like bug prediction or code completions. So if you were yourself like a first-year PhD student and you could give yourself an advice, what would that be?
So are you asking about software engineering in particular or in general?
Well, feel free to, you know,
yeah, so
interpret your question.
Yeah, right. So for software engineering, I would say the most important thing in my view is currently we don't understand how to represent software, right, for machine learning. And every new paper is kind of proposing a different approach in an ad hoc and coarse-grained way, right? So some people are feeding the like source code as tokens, others are considering ASTs, others are considering AST diffs, others are, you know, are thinking about like, you know, control flow graphs now. But it's very ad hoc. We don't know which of these are actually working and which are not working, and how to represent source code or even programs, because a software program is not only the source code, there's also a lot more. You could also think about the visual aspects, for example, right? So I think as a community, we need to think about, like, step back and think about this. Like, how do we actually represent software programs for deep learning, right? We don't know that yet. So instead of just proposing new ideas and not even comparing with others that have been proposed, maybe we should step back and kind of do a thorough, maybe control like empirical evaluation of what actually works. Because as I said, there are so many different parameters that you can play with, right? When you're training these models, and you make one change in any of those, everything can change. Everything changes, right? So maybe like a benchmark in which you could have some degree of control on all these very dependent variables, and then only change maybe how you represent your source code, and see what the effects are, right? So like a large-scale empirical study of what actually works better in terms of representing software programs. So that's something that will be, I think, essential. Like we need that in order to kind of move forward, because otherwise it's all guesswork, right? At this point.
That's actually a very good point, because like it was a point that was made already in the first panel this morning. Because like deep learning models are very good at learning associations of data, and but they can't explain why they took a specific question. So yeah, working more on this abstract representation of the problems that we need to solve, that's definitely a good point. Thank you.
And control experiments and comparisons, right? Because I don't see a lot of that. It's like everybody's coming with new ideas, but we don't have any benchmarks to compare against each other. At least in software engineering, I'm talking about software engineering. Probably in other domains, I don't know how it is. Maybe it's better. Yeah.
Okay, thank you. Since we are running out of time, I think we should try to wrap up this very interesting discussion. So I would like to propose for each of the panelists to give a 1 minute shot at the latest, greatest idea that students should start researching right now. So who wants to start? Yeah, please.
So just off the top of my head, perhaps I can give a negative suggestion. So what they should not study. Because this is actually connected to something that was, I think, also touched upon during the other panel this morning, earlier on today. I think, yeah, there's been a lot of excitement about applying machine learning and neural networks specifically to problems in software engineering. And I think we're already to the point where sometimes there are cases where people don't ask themselves, but do I really need an approach like that? That is, has, of course, great advantages, but also certain shortcomings, and we've touched upon them, like problems with robustness, and then the problem that about understandability of a model and so on. So sometimes one should leave an approach based on machine learning as a last resort rather than first option. Or in any case, at least I think it's always useful to think of possible alternatives to solve the same problem and use them as baselines, because this is also something that makes it easier to really understand what we have achieved, to assess the quality, the usefulness of whatever we have developed.
Okay, thank you. Matt?
Okay, I'm on mute. Yeah, it's a really good question, and it does seem like one that for whatever reason is easier to answer in the negative than the positive. But like as a general area that I think is likely to lead to productive output and impact. Identifying cases where like we can do a reasonably good job specifying in a partial sense like what we want from not just a model but from an application that makes use of a machine learning model. So like one sort of pitfall might be focusing too much on like just the machine learning component and forgetting about the larger application or system that it exists and is a part of, and making use of the resources that are available on an application, sort of by application basis. So while in general, like, you apply machine learning because you want automation and you want to sort of outsource some of the things that have traditionally required, human input to a machine. It might not always be the case that like you can, or you have to ignore sort of having a human in the loop, or like having some kind of lightweight oversight from human beings, and being able to sort of work that into that and similar sort of advantages that might exist in the application context into a framework of specifying like what you want out of the model. I think is a promising direction, and that's an area that I would definitely want to look into if I were starting out.
Great, thank you. Ali, are you still online?
I think Ali had to leave.
Oh, okay. I'm sorry. Yeah, we are running out of time. So Zico, would you like to close the session, the panel, with your remarks?
Well, I'll offer a different perspective than a robustness work for this one, given this is a software engineering audience to a large extent. Most software engineering is characterized as sort of first principles building of software, right? Where you have an idea, an algorithm idea, you implement it in code, and if you implement your logic correctly or there's no flaw in your logic, it will work. Machine learning is phrased as you have no idea what the logic is, you're just given examples, input, output examples, and you let the computer figure out what the program should be to a certain extent. There's a huge swath of middle ground here where you can specify some things about a program, but not everything. And I think we're only getting started in this notion of, can we design programs to kind of where you specify this control flow and structures and parameters, but just leave some things unspecified. And those unspecified things you train with end-to-end backpropagation or some other means that we haven't discovered yet. This is a hugely sort of untapped area of work, both from the machine learning standpoint, and I think also from software engineering standpoint. Maybe there's more progress on it there, but I'm not really aware of it. And I think we can do so much more to merge these two paradigms, each of which have strengths and weaknesses. So if I was to recommend, someone just starting out in their PhD, looking for a topic, this just has to be a major thing that's going to affect the next several years of software development and of machine learning, because we are so diametrically opposed in the traditional application of these things that we just have to explore the middle ground.
Okay, great. Thank you, everybody. So on this high note, I would like to thank the speakers and the panelists, and we are closing it and looking forward to working on these interesting topics. So thank you. I'm closing. Yeah. Thank you.
Thanks for running. It was a lot of fun.
All right, let me share my screen for the final remarks. So I think overall this edition was a success. Thank you all for joining us. And if you want like some numbers, there were like more 100 people registered, and overall was trying to track the participants over the sessions, and there were quite some. So thank you all for making like DeepTest great. As for the new editions, like we have some ideas. Things are not finalized yet, of course. So probably we'll try to host DeepTest 2021 in ICSE in Madrid. We'll see whether it will be a physical conference, a virtual one, or a hybrid format. So we'll wait for ICSE's guidelines. As for the current format, I think there would be some debate whether to keep like the current one, or whether to introduce proceedings and then prompt committee, or like maybe like to see if we have the numbers to move towards like more a conference level size. Maybe not now, but in the foreseeable future. So the most likely options to date, like as far as I'm concerned, is like introduce like proceedings and then actual programming committee. And the dates, as for the dates for a submission, I guess they would be similar to the ones for this current edition of DeepTest. And we'll probably make a survey and share it with all the participants so that, you know, we can collect feedback and then comments. An idea that I got from Amasar, looking at some of the presentation yesterday, they want to introduce a sort of shadow PC in which essentially knowledgeable students and postdocs can actually get involved into reviewing papers so that like more senior people can actually give them feedback, so we can actually educate some of the young generations into these academic you know, procedures. And also given like you know, the progression of this field, we also, it would be also like a good idea to fetch from this young generation, because they're very knowledgeable about this new stuff going on. So this is pretty much you know, everything on my site. Feel free to, you know, add more stuff, and see you at DeepTest 2021.
Thank you, everybody.
So I think we can leave the room chat open for a while for people to chill and keep like you know interactive. And I see like rounds of applause coming. Like, we also, you know, love you very much. It was great to have you. Hi, Matt. Stay all safe. Hopefully we'll have the next edition live in person.
It would be wonderful to see everyone in the flesh. Yeah. Thanks, guys.